Hello everybody, welcome to another stream. How are we all doing? Happy Sunday. Hope we're all doing good. It's very warm here. Just been enjoying the sun. So what are we working on today? Let me draw my window in a bit. So, let's try something like that. So today what we're doing is working on the graphics subsystem, like the GPU bit. So we have a window here and it runs a single compute shader. But what we need to do is firstly fix some, before we write any more code, we should really clean up one aspect of it because we're just going to be producing more mess. And then the next thing we'll do is actually implement resources so we can have buffers and textures and not just a back buffer, right? So yeah. So what I want to start off doing is go into the source GPU backend Vulkan, right? So we do have some to-dos in here, but they're not overly, we don't need to do them right away, like allocate the stuff with a temporary allocator rather than using the call stack, or what are the ones we got? Yeah, the number of resource descriptors we have doesn't really matter right now. We need to write all our resources out into a descriptor set, but we don't have any resources yet. This is what we'll be doing later. Timelines, semaphores. Yeah, in future when we actually have multiple stages that we're rendering to different textures, we definitely want to fix this problem. Yeah, right. FIFO as well, we should probably fix that at some point. But so the issue we've got to fix is this, and I don't think I've got a to-do label for it because it's like really obvious for me. And that is every function call in Vulkan is not what it seems. So effectively in Vulkan, anything that so you have three layers of things, right? You have the VK instance, functions that take a VK instance in as the first argument, right? And functions that take a VK device, okay? And functions that take absolutely nothing in as the first argument, right? Okay, these are the three different types of functions that you can categorize in Vulkan. Either it belongs to absolutely nothing, it belongs to an instance, or it belongs to a device. And bear in mind, a device belongs to an instance, right? So effectively, when you call you have this, when you download the Vulkan SDK, you get this thing called a vulkan.so, or in Windows land it's vulkan-1.dll, right? So you get vulkan.so in Linux, and then on Windows you get vulkan-1.dll. So these guys are not the driver. Like, they're not the Vulkan driver, they're a wrapper around the driver. So what happens is when you call a function which takes in an instance argument, no, I think let's talk about the device one. Yeah, this one's the easiest one to speak about. This device that you have, this logical device, like when you call a function, for instance, like I don't know, VK create image or create buffer, right? And you pass in the device and then the other arguments. What's happening when you call this function is it's not calling directly into the the Vulkan layers, or directly into the driver. It actually has to go through a certain step. Hey there, Buffer Overlay, how you doing? Yeah, man, not doing bad, doing pretty good, thank you. Yeah, it's very nice and sunny here, so I went out for a walk today. I made a roast, and the roast came out really good actually. So I'm super happy about that. So I've eaten very well. It's very warm though, so I don't know if I can wear the headphones and hear the music with you guys, unfortunately, because I'll just get too hot and then my brain will start not working, which will not be a good mix. But yeah, hey there, Not So Red. Hope you guys are doing good. How's the week been? Or how's the weekend been? Whatever, all of the questions. As usual, nice cold can of Pepsi Max. So, I'm not sure if I fully understand this problem where I can explain it. So let me just quickly do a bit of research. But I dropped the link in last stream because I think someone was asking about it, so I just threw the link in. But Vulkan dynamic loader. So Vulkan. So the issue is, just gotta find the blog. There you go, this is it. So it's done by Arseny, the guy who works in Roblox. Almedes Ransel, thank you so much. Thank you, sir. Appreciate it. Oh no. You're forced to write just saying, hey? For a school project. Damn JavaScript. Oh. Yeah, to be fair, when I first started programming, JavaScript was like I actually really liked it. And I think when you're learning programming, it's a really good language to sort of just get understanding if statements, for loops, and things like this. But when you actually know how to program, it's hell, right? So yeah, I highly recommend you read this if you want to understand fully. But effectively, when you call into a standard Vulkan function, it calls into this vulkan.so or .dll, depending on your platform, which has inside essentially like a hash table lookup based on the device and the function you actually need to call. So every time you call a Vulkan function, it actually goes into here, looks up the function that you actually need based on the device, and then gives you back the actual function points you need to call, and then it'll call it, right? So yeah, it like introduces a bit of overhead. So what you can do to reduce this overhead is simply fetch all the function pointers when you initialize the graphics backend or the GPU backend, and then we can just call those function pointers directly. And now it won't necessarily always go directly to the driver, because Vulkan has like a layers system where you can have layers that intercept the Vulkan function calls. And this is how people like reverse engineer games, because they can intercept the Vulkan. Well, this is how some tools work to debug Vulkan, but also how people can reverse engineer how games are doing graphics, right? But yeah, so we're going to go ahead and actually load all the function pointers that we need, and there's 3 layers to this. Remember, there's loading the functions that are not related to anything. There's functions that are related to an instance, and functions that are related / need a device. So if you open up the Vulkan Vulkan core, what you'll find is there's a couple of functions. There's a getProc address, which stands for procedure. Oh, wait a minute. Maybe it's not called that anymore. There you go, get instance proc address. Okay, Here we go. So what we want to do before we include any of these Vulkan headers, what we really need to do is say, hey, we don't want any function prototypes to avoid, especially if you're working on a team of people, you want to avoid people not doing it this way, because so there's a thing called prototypes, function prototypes. There you go. So we're going to define the fact that we don't want any function prototypes, meaning it won't give us the ability to call functions directly. Instead, we have to load the function pointer and then use these. In our programming courses, we learn C#. Oh yeah, it's more like you learn like OOP and stuff like that, right? And surely it must be like data structures and algorithms, maybe? I'll probably have to work with JS for so long there is no graphics visuals in my area. Ooh. Yeah, maybe you can apply abroad and do a work from home thing, because nowadays more companies are accepting of people working from abroad. Yeah. Like in our company we have a couple of people from Sweden. And so like 3 people from Sweden, so well, it's not in the company, just in our team. But yeah. Our teacher didn't work in too many languages. Yeah, I see that reason. The only language I like working in is C, right? So I can definitely see that opinion. Hey there, Zen. How you doing? Yeah, man, it's going good. We got a window open. We're just about to we have a window that renders stuff to the screen. So we're simply just getting some more of the essentials in, really. So we don't really have any textures or buffers other than the swap chain texture. So we're just adding support for more textures and buffers today, and probably doing some proper sync code so we can do more than one compute shader dispatch. So it's going really well for like 3 streams. Also, it runs on Windows as well, so it's all good. Oh, not uni level, right? Okay, I see. Well, at least you're doing programming in secondary, and C# at least, right? Something with types. It's so warm already. I can't deal with heat. Right. So, how are we going to deal with this, right? So, if we compile anything now, it's going to complain and cry. Right. So what we actually need first is a new OS abstraction, and that is a dynamic library loading. Now I think I've made one of these in the past. Could I go and fetch it out? It's so minimal, it'll be super easy to actually just do it from scratch again. So we need a way to load a dynamic library and then also load function pointers from that dynamic library. So when you make a dynamic library, you can either link against it or you can manually link against it at runtime. And this is how people create optional dependencies or plugins in C applications. Is they will do it this way. So we're going to go into our os.h, and we're going to make our right. So we'll probably type def a new structure, which would be called os DLL for dynamically linked library. And I don't know. Yeah, let's try that. I so want to listen to this music you guys are listening to, but I just can't. It's too warm. Let me guess, this Vulkan will be used for 2D sprite drawing. No, it's going to be used for 3D. We're going to start by doing 2D because I want to get a debug UI, right? So we can actually tweak some values at runtime without coding. Like, I probably want to get hot code reloading as well, but I think, yeah. So we're going to be starting off by doing a 2D renderer purely for UI, and then afterwards we'll actually do some 3D R&D. Yeah, everything is built for a reason in this project. Because otherwise I'll basically be building an engine, right? OS, DLL, so it could say open, right? Open and close, I guess. Right, so you need a const char star path, and then you have a close. You can have a ball. So I don't think there's actually a way to get an error back, like a proper good error back with these DLLs, I think. Let's have a think. Some assignments are actually quite hilarious as we need, such as we write so and so as a container class to get set methods. Ah, I know, right? I know. Like getters and setters. Oh my days! It's funny that in C# they made properties to shorthand getters and setters, but it's like what? But you can make it even shorter. Just make it a field. you know. Uh, what kind of game are you making here? Or is it the plan that it will unfold over many streams? So I do want to make a plan. But the plan, I don't think there's much of a plan. Point making a plan right now. I think the idea is I want to do some 3D graphics, R&D, find an art style, and something I can use to actually make a game in 3D, and build a tool or something. And when we have an art style that we want, we can then use that as part of the input to figure out what game we want to make, right? And then from there, probably make some tools, and then actually make the full game with the tools. Yeah, building it and see how it turns out is very easy. Very easy just to let things just go on and on. I want to try and plan something and sort of scope out, like, this is like, try and underscope it a bit, and maybe say, hey, I want to make this game in like 6 months or a year, and then like at worst it'll be 3 times that amount, right? I think that's the plan. Yeah, see, I think as a programmer I really like programming and everything, but also I like being able to visually see things and take a break from just reading stuff coming out of a terminal, and being able to visually have a play is actually see the thing you're building first. I think would be better, and understanding the feeling of it. Kind of weird that languages don't tend to have const when public mutable. Sorry, const when public, mutable when private qualifier or something. Right. Yeah, I guess when it's private, you typically want it mutable anyway. Right. Hey there, new moderator. How are you? How are you doing, Perry? Perry, sir. Welcome, welcome. Oh, I see. Right. Yeah, I see what you're saying. I was reading it as separate constructs. I see what you're saying, as in one construct. Yeah. Yeah, that's an interesting take, especially in a language like Rust, right? where we have modules or something like this, and it's not just header files. So the other thing we need is a DLL. I forgot what name we want to use here. It's kind of like we want to find a function pointer, right? I don't know. Maybe we can say get function, but I'm not sure. We'll just write that for now. But it's not really function. It's like find symbol, isn't it? That's what it is, because you can get global variable as well. So, and then find makes it seems like it actually takes some time, right? It's figuring it out. Because they get symbol, but find maybe. So we also need DLL. So we need so I could return like an out pointer, or I could just say DLL. Let's say mute or something, I don't know. You know what? This would be an out pointer. Yeah, something like that, that's what we want. So I'm not sure about the Boolean, so should we just investigate so there's DL open. So we can be a man about this, right? So I think with DL open, does it set the error no, or no, it returns you a pointer, and I don't know if there's a way to get a good error about it. Like we could stat the file name and then see if the file actually exists and then give back a proper error. On error, if the file cannot be found, was not readable or wrong format, causes errors in loading, right? It's not really a nice API, so we could just distinguish that by searching for if the file exists or not. And you can distinguish these manually, except for this one here, or maybe you can do that manually if you know the format, but that's just more work. But for now, I think we'll just return a Boolean. We can always make it better, I think. Have I tried Helix editor? Well, like, is that a text editor? Because I know Helix is some version control system as well. Hey there, Davros. How you doing? Hey there, very much. Good to see you. Oh, I've never heard of it as a text editor. And hey there, Turd Beaver. Right. So we are going to implement this on both Windows and Unixes here, right? Because it's a very small function, and if it's slightly wrong for people who are following on Windows, it's just going to be compile errors you should be able to fix, right? It shouldn't be too much rocket science. So let's just throw this boy in. So Linux, how do you do it? So there's a function called DL open. So for that, you need to include dlfcn.h. dlfcn.h. Ta-da! And what you want to do is get back the this is the handle or something like that. I don't know. Library. Lib, I guess. So you want to say dl open, throw in the path, and if lib equal null, what we're going to do is we're going to throw out return false, and then anything else after this is true. And then we're going to set DLL out to be .raw, I guess I call it, to be lib. Okay. It expects 2, eh? So the second argument is flags. Flags are gonna, oh shoot, we want to get, so do we want to be lazy about it? I think we do. So lazy means that it's not going to resolve all of the symbols. Only when you fetch them will it try and resolve symbols. So that means in the DLL itself, there is code, and inside that code there is function calls. A function call can be a call to another dynamic library function. And you can either, when you DL open that library, you can get it to go over all of the function calls throughout the whole library and patch it in memory and get it to retrieve the actual function. Or you can do it in a lazy way, which means when I execute the code for the first time, what we're going to do is we're going to actually patch the code when we run over it the first time, and that's how typically things actually work anyway. You can change it when you compile the code, I think, but typically this is good because it allows you to only load the functions that you actually need and not pay the cost up front. But you may want to do it if you want it to be more predictable, right? And the library's small or something. Right, so this now says the value specified environment variable by now. All undefined symbols and shared objects are resolved before DL open returns. So that's the opposite of lazy, right? One of the following, lazy on now. Local and global, let's read these guys. I think there's another one we need to OR it with, from what I remember. Or Bayes and Volk. So the thing is about using Volk is like, it's not actually a hard problem to solve it yourself. And if you're using Volk, I believe you're basically loading every Vulkan function you probably don't need. And it's very easy just to hand roll it yourself. And that's what we're going to do here, hopefully within the first hour of the stream, including writing this DL abstraction on the operating system. The thing is about the Volk library is it's a prime example of solving a problem generally, how it becomes far more complicated if you have to solve it generally. If you read through the code, it's a lot of code. Whereas if you just solve it for the functions you need, it's actually very simple. But yeah. But if you use the C++ Vulkan stuff, it's actually in the C++ headers as well. They have a function loader. But yeah, and I think Volk is for C++ as well. Right, global, the symbols defined in the shared object will be made available for symbol resolution of subsequential loaded share objects. Local, the default is neither specified. Symbols defined with this shared object are not made available to resolve references in subsequential. Right, so this means if you say global, you're saying the next time I call DL, like the next time a symbol is loaded, it can use the symbols that are within this DLL. Now, because the way that I think we're going to be using these DLLs is we're using them for like plugins or to specifically fetch functions that we want. So if we're going to be coming across, so if we're going to have to do a lookup for a function that hasn't been loaded yet, we don't want it to go and search through these optional dependencies that we have loaded ourselves manually, because we're specifically interested in a few functions, right? So I think saying local is probably what we want. I think that's the other one. Let's plop that one in. And there we go. So that should be loading. DL close. DLL dot raw. And then find symbol. Right, where's the other bugger? What is the other one? I've got to find it now. DL sim. This is it. Right. So DL sim. Hey there, Paya. How you doing? Good to see you. How's things been? How's things going? And then we want the name of it, right? And then you return like that. Pretty sure. Yeah. Voila. So there we go. That right there is a dead basic DLL abstraction for Linux. But what we need to do is, wait a minute. Got that wrong. So what we need to do now is actually implement it on Windows. So we need to say OS, Windows. We're going to grab these guys. And then we're going to plop down to the bottom. Drop it in the right place. And then, so if we, so I think it's called like load library, right? Win32 load library A probably, right? And you probably get like a, right, you get a H module. Pretty good. We finally have some sunshine today. I know, right? It's been super sunny here as well. It's really good. Like, it's been like 30 degrees. Nearly. No, it's reached 30. Yeah. Past couple of days. So I went out for a walk today in the sun, sat outside eating a roast for lunch. Yeah, it's been good. Hacking together some Unity prototypes. Oh yeah. Also, you're prototyping in Unity to see if you've got any game ideas. Yeah, that sounds like a good idea if you want to try and figure out if a game mechanic works well before building everything else, isn't it? UK's for plebs. Hey, we get good weather only for like 2 months in a year. Leave us alone. Right, so we want to use load. So we want a H module. Load library A to say it's an ASCII path, right? None of this Unicode crap. None of these special things. So if the H module is, look at the return parameters. If it's null, then it's an error. Perfect. Return false. If not, throw it in there. That should cast just fine. Then we should say, what's the opposite of load library? Free library. Free library. Then to find the symbol, get proc address. So we might have to cast it, I'm not sure. Is there get proc proc address. Right, it's just that. Okay. Function. Yeah, we might have to cast it into a void pointer because it probably comes out as a void function pointer thing. So we're casting a void pointer. Let's see what that's defined as. A farp rock. What is a farp rock, people? Please tell me what this farp rock is. Such a good name. Okay, Rust is super helpful for this stuff. We gotta love it, Rust. Oh no. Wait. Maybe we can get there. Right, watch this. This is gonna be the most weird way of figuring out what it is exactly, just for a bit of fun. Heh 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 heh. Is there a Win32 thing? I see what they declare it as. You know what? This is too much work. I don't care what it is. It's just a pointer, people. All right, it's too much work. Yeah, Rust is really nice. Like, if you're coming from like web development or Python or whatever, or if you just fancy a nicer language and not dealing with some of the rough edges of C and C++, it's a nice language. You know, Cargo is pretty decent to sort of like, you know, just to easily build stuff and everything like that. But yeah, I think the culture around it is just a bit, yeah, and like the memory safety thing. Just I don't think it's, yeah, it's good, but it's helpful for people learning, I think. But in the long run, I think the restrictions it gives you as a developer is not helpful. But yeah, if people use it, that's cool, and like it, that is also cool, but it's just not for me. Do you know that is valid C? Static constants, const. I don't think you can declare multiple. No, it is valid C, but the compiler might warn you that you're just specifying too many consts because you've specified that int is 3 consts 3 times. If you stick a pointer in there, it might be fine. How are you learning C-lang? I'm not relearning C-lang, I pretty much know it. Because I've also written my own C compiler as well, so I'm not really learning much C anymore. Although I did learn some of the intricacies of C and then completely forget it because there's some weird bits in C. Right, so I just want to say for people who have developed, who are maybe following along on Windows or something and implementing this and they run this, or maybe if they download it later and run it, this might not compile, right? But it's probably like just a tiny bit off of actually compiling. Yeah, that's it, you know. But anyway, we've got the abstraction now, so now we can move on. So what we need to do is we need to make our own, in our Vulkan backend, we're going to have the operating system DLL, and this is our Vulkan DLL. Well, let's call it DLL. Right. So when we create the So up here, we're going to define a GPU VK DLL path. What is the path to the DLL? So for this one on Linux, it'll be vulkan.so. On Windows, it is vulkan-1.dll. I think there is a -1 on Linux, but you can just use vulkan.so. Then what we need to do is we need to load this library. So the first thing we're going to do is say gpuvk.dll. Wait a minute, that's the last parameter. We'll say os.dll open. We're going to open up that path and load that DLL, please. Then we're going to have a core assert. Core assert, the condition is DL open is true, and then failed to load Vulkan dynamic library. I'm going to say Vulkan library, right? Yeah, in future, we maybe make that error a bit better. So after we've got the library loaded, this is where we can actually load all of the function pointers from the DLL and everything. So the plan is we only need to load a few. So there's 3 different types of ways of loading, right? There's OS DLL find symbol, which is the new thing we've just made. For that, we'll pass in this, right? We'll pass in the name of it. So the name might be, in this case, VK create instance. Yeah, this one here, right? Right here. It doesn't need an instance, or it doesn't need a device. So these ones are just standard, right? You'll be doing something like this, and you get out of the function pointer. I think far is related to the far or near pointers. So it's just an old ass backwards compatibility name. It's really just a pointer to the beginning of a procedure. Yeah, I was just trying to more interestingly find out whether, like, if it was actually a void pointer they give you or a void function pointer, right? I was just interested to see the exact specification. But yeah, the naming is interesting for a lot of stuff I've done. Man, I think that bot speaks a bit too much, but there we go. What's that one time? So there's that way of loading a symbol, which you'll get back so we'll load that into a VK create instance thing inside of the GPU VK. So we're going to put all of our function pointers that we actually want to use in Vulkan inside that structure, and they're all going to be next to each other in memory. So it's pretty easy to go and fetch those function pointers. So that's one way of loading them. The other way of loading is by using the get int vk dot, and we'll be like for instance saying create buffer as an example. We're going to load that one in, and this one's going to be gpU vk dll. No, sorry, not the DLL. We pass in the GPU VK instance, right? Because it takes an instance as the first one in the name. And then the final one is actually no, this is the wrong one. Damn it. Create device. Because that one takes an instance in. Whereas create buffer takes a device in. So we'll be using the get device proc address, and that's taking a VK device. So these are the 3 different classes of ways of loading a function pointer in Vulkan, 3 different levels to it. So how are we going to do this? What's the easiest way? We could hand type out like this, but it gets extremely repetitive and it's a bit crazy. But you can also solve it with another crazy method, and that is with macros. So what we're going to do is use a technique called X macros. So all we need to do is define a list of all of the arguments that we'll ever want. Sorry, all of the functions we'll ever want. But we're gonna say define GPU VK function list. Okay. And then we're just effectively what we're going to do is have a load of other sub macros in here. So the technique is called X macros. If you search for X macro into Google, you will find there's a Wikipedia article on it. It explains exactly what it is, but we're going to show you what it is instead. So you remember there's 3 different tiers, right? There's essentially like one that you load directly from the library. There's instance, and then there's device, right? So I think we'll say library, then we'll say instance, then we'll say device. So I think I might say, wait a minute. So I'll say GPU VK library function instance function and device function. Okay. So let's just get a few in there, and then we'll add more that we need. So these get proc addresses. I think they can get loaded directly from the... We'll see. Let's load these ones from... Alright, so VK create instance. There's definitely one there that we have. And then we also have... What's another one? The instance one we could say is create... Let's say enumerate physical devices. We're going to need more, because there's one that takes an instance in. A device level function. What other device level ones? So device one will be like VK submit, because it takes the device in as the first argument. Okay, so you don't need the commas here, you just need a bunch of backslashes, and these are effectively a bunch of macros that are going to get called and unraveled. So right. Hey, Selective Duplicate, I'm still chilling with day 1. Today's stream seems early, usually streams during my bedtime. Oh, are they? Oh yeah, Sundays. Sundays I start at 4. But yeah. Awesome, good to hear, good to hear. Yeah, if you get stuck on anything, just yeah, feel free to ask, and make it a little bit clear. But yeah, awesome. I think if you're not running on Windows, yeah, like the Windows one on day 3, you can pretty much like maybe skip that one if you don't care. But yeah, day 1 and 2 are really good. Yeah, we're on 4 now. Yeah, it starts at 4, Perry. Unless I'm late, which I try not to be anymore. Didn't my Ubuntu set up on my laptop. Awesome. Good to hear. So this function list, every time you use it, you've got to declare these 3 macros at least. Bear in mind, we will be duplicating these macros and adding more functions. But yeah. So there's a couple of places where we need to stick this. There's actually 3 or more places, I think. So the first place is we need to put all of them. Wait, do we not have the OS? Damn flies. We need to put the OS. OS/OS. That's what I want. So we'll call the function list in here. We're going to define those 3 macros. So that this library function one. So we're going to say, hey, how do we want these macros to be used when we invoke the other macro which contains the macros, right? It's very hacky, but it's a good solution. So we're going to say, hey, we get a function, or we get a name of a function, and what we're going to do, function name. What we're going to do is we're going to say here's the awesome part about the Vulkan header. It is quite big. It's like 17,000 lines of code. But they come pre-bundled with, so because we don't have the function prototypes now, they still give us the type def for the function pointers that we're going to be loading. So all we need to do is prefix it with pfn underscore and then stick the suffix on the end. Then we've got the type of the function pointer. So all we need to do is say, hey, pfn, then we glue on the fn name, and then we say fn name, because that's going to be the name of the field. So we can refer to it in the source code as simply ggpuvk, then the function pointer, or then the name of the function, which is the function pointer. Okay, so all we have to do is do that for this case only. It'll be different inside the code base. Then we're going to undefine them because we want to make sure we can declare them later, because it is a error in C if you define something more than once. So these are all so declare, use X macros, to declare all of the function pointer fields all of the Vulkan function pointers as a field in this structure. Okay, so we should probably put a comment on that list thing up the top to say this is an X macro that we use to declare and load all of the functions from the Vulkan dynamic library and driver, something like that. And then we should basically just say, like, you know, search for this to see how it is used differently in each place, something like that. So when we just say, like, if you want to use a Vulkan function in a new Vulkan function in the code base, add it to the list below. Very cool. I know these stuff windows are a pain. Oh no, did it do that? Ah, oh, Twitch keeps effing around with my damn things. Oh, it doesn't. Okay, that's fine. Oh, it's your time zone. Yeah, that's good. Yeah, they're correct on my screen. Yeah, no, sometimes on Twitch, if I say set these on like vacation mode where I skip a week, it will sometimes set them back to a Monday. And it's like, what? Anyway. Hey there, Wajilla, how you doing? How's things going? Welcome, welcome. Oh. So, now, this is where the fun begins. Anakin Skywalker. So what you need to do is take this, and now we need to use it in 3 different places, because remember, there's 3 different ways we can load a function. It's either using this find symbol thing, which we've just made, get instance proc address, or get device proc address. So obviously we can only do these when we have an instance created, and this one we can only do when we have a device created. So the first one needs to go here, right as we open up the library. We need to literally copy this line and do this, right? So we'll say fn name. So we say that.fn name equal, right? And then we turn it into a string with the hash. So if you prefix it with a hash, it has to be a macro argument, right? If you prefix it with a hash, then what you're saying is turn into a string for me. So that will load it. But the problem is you don't know if it's loaded properly or not. So how you fix that is you simply, so you got to put backslash here, and backslash there. And then you're going to say core assert, because that's what our assertions are called. Make sure this is loaded for me. And you say if not, failed to load function from, and then we put the Vulkan GPU VK DLL path. Yeah, put that in there. That's always a string, so we can just put it in there. That's string concatenation. Where it has to be the strings have to be static strings, right? It's just a macro, so it's a static string. You just paste that in the file, so it will join up nice and good. Failed to load function from failed to load string. Oh, we can just do it here. Stringify fn name. So that's gonna use the preprocessor and the parser and everything to effectively make all of that into a single string, literal, without any runtime argument stuff. So that's cool. That'll be a good error to see. We can see that error in a bit. Hey there, Lean Mean Gene. How you doing? Do I have commands? Yeah, I've got some commands. But they're mainly just it's mainly to provide links, like an easy way to drop links into the chat related to the stream. But there is, yeah, basic ones. Yeah, because I haven't really programmed my own bot, I just use another one. Makes it easier that way. So the rest of these guys don't need to be here. So right, that's the first one loaded. So we just want to say like, you know, load all of the function pointers from the library, from the Vulkan library. Then we say not the instance or device ones in brackets. I don't know what that error is. It goes off the screen. It's not very handy, but we'll see in a minute. So the next one, we'll get this at the ready. We'll have to put it in the right place. So after we load the instance, so we'll have to move into the right place after. So these ones are empty now, but now it's the instance one. So this one's got to use the get instance proc address, and this is going to load it from the instance instead. Same sort of thing, but failed to load Vulkan, wait no, from the Vulkan instance. Yep. Cool. And there's one more of these guys. Wait, so load all the function pointers from the Vulkan instance, not the library or device ones. From the device, not the library or the instance ones. Yep. And this one takes this down here. So for the device ones, we're going to use vk get device proc get the vk device. Okay. So now we've got all the X macros sorted out. We just need to put them in the right place. So remember, it's just doing this. Right, it's just generating a bunch of these with some assertions to check to make sure the function actually got loaded. So let's go ahead and put it in the right place and fix all the errors. So, right, so after we create the instance, we then want to do a load. Yep, of all the instance functions. Then after we create the device, create device. You know what? I think what would be a good idea is if we put it inside that scope as well. Voila. Very good. Right, so now we're going to get a ton of errors, so we probably want to hit compile and see what that looks like. See why it doesn't like it. You know what? Let's run it from here so we can actually see what it looks like. Scripts build sh. There's no, oh, there is a title one. Okay, so let's see where our X macros are going wrong. So straight away, so you know, let's skip these ones, but let's solve the things we've just been writing for, because so it's saying it cannot convert a void into that type, right? So obviously we missed something. We forgot the cast. So every single time we we're in the interrupt, that's why. We'll come back to this one. GPU, Vulkan, okay? So when we do this get proc address thing, we've actually got to cast it into that pfn, and then we glue the function name on it. So it casts it into the function pointer type. And that needs to happen on everything. All three different levels, right? So that'll fix that. Oh, I need to glue it. Ah, damn it, one off. Rightio, very good. So now the rest of the errors are complaining that, hey, we're trying to call this Vulkan function, it doesn't exist. Because remember we said we don't want any of the function prototypes in Vulkan anymore with this VK no prototypes. We're going to load them ourselves, so we can just call directly to the function that we actually need to, rather than going through this internal loader, right? Hey there, Molly Niche. How you doing? Welcome to the stream. So what have we got? How do we solve this problem? So what we need to do is we need to move these guys into that X macro function list and then simply prefix it with a GPU VK. So basically anything that has a VK, like a lowercase VK, I don't know how I want to search for this. Right, vim search for lowercase. Backslash lowercase c. Okay, so let's say no, it didn't work. So I'm saying any lowercase character. Okay. Help / ignore case. Thing is, because I've got that. I've got an option on which basically disables. It's called smart case, I think, where it's only if you put capital letters in will it search for capital letters, but if not, it searches for either capital letters or lowercase letters. Oh, maybe I can do it like that. No. Yeah. Smart case is handy, except for in this one case now where I need to do this. Did your face is so familiar appearance to Ukrainian singer from the Unsleeping Band? Oh. Would you want to send me a link and I'll take a look? Apparently people think I look like Harry Potter as well. Casting my spells in programming, you know. Could you do VK? Let's try it. VK A. It worked. Oh, so you're saying uppercase. Wait a minute, if that's a suffix. I don't even know what's going on right now. Does that work? Ooh. Oh yeah, but your one will work better. Because you're saying the next character. That's what I thought that one was doing, but it's not. Genius. Right, thank you so much. Right, so what we want to do is record a macro. Well, not really record a macro, just simply do gpu.vk dot. So we can use the function pointer instead when we have it, right? So we're just going to go through and get that in. So this one loads the function pointer and then calls it, that's fine. Enumerate physical devices, cool. We still need to go over all the errors though and pick them up, but we'll come back around because we need to put them in the list. Is the music still going? Quite a lot of functions here. This is why I wanted to fix it now, because it means that in the future we'll have less of these to go over. You know, it might have been cool, like, you know, write the whole project and then benchmark it before, then benchmark it after, and see how much of a difference this really makes. But oh well. All right, full circle, we made it. So, okay. So now the next job is we need to get all the functions that we actually want and put them in the X macro thing. So this is another library one. Enumerate instance layer properties. Instance layer extensions. Create instance, that's already there, yep. Get instance proc address. I think that's an instance one. Looks like it. ggpu vk dot. It will be there. Already got that one. So for an instance function, physical device memory properties, yep. Next, device format properties 2. Get that. Queue family properties, get that. Create device, get that one. So after we've got the create device, now it's just the device functions to do. Alright, take a look at that link. This looks like me. Maybe the nose and the beard. Maybe. Yeah, I see sort of a resemblance. The hair is different. The eyes, maybe. Don't have eyebrows. Sort of. Like, yeah, generally different enough though. Hey there, Silvercore. How you doing? Yeah, there's some resemblances. If you were to compare features, but overall I don't think. Maybe because I know myself so well, right? Bum 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 bum. Right, device queue. So that's a device function. Plop that in there. So this is a create xlib surface khr. Right, what is this guy? So I could have forward declared this function, you know. I just realized that now. I can remove the whole xlib header if I wanted to. I could do that. Should we try and remove the whole xlib header from this compilation unit? I reckon we can do that. Seems like a bit of fun. No, I'll do that later. Right. To do forward declare this function and the used xlib data types to completely remove the xlib header from this compilation unit. This must be done after we move away from single compilation unit, from compiling a single compilation unit. Nice one. Yeah, so basically this is only used in Linux, right? It's not used in Windows. So in that header file, we need to make another function list specifically for X11 or for Linux. This one is a instance one, so that'd be a GPVK instance. Then we also want to load this one, which is get physical device representation, whatever. Nice. Cool. Now we need to do the same thing for the Windows side of things. No, so we could say OS at the end, right? Operating system. Because otherwise you got to do Linux. You can't if-def inside of a macro, which we'll have to do down below. So this one needs to be the Win32 ones. Just yoink these out of there. Yoink. So Win32 create surface and Win32 get present queue support, something like that. And then we take this OS thing and we call it right at the bottom of this thing here. Right, so now depending on the operating system, it will load different functions, right, from the instance proc address thing, yeah? So that's doing good. Let's continue the search. Nice, those disappeared there. Let's keep going. Create command pool, that needs a VK device. Allocate some command buffers. Oh no, I lost it. Right, we're back. Create a semaphore. That's a device one, okay. Bug that one up. Create a shader module. That's per device. Create compute pipelines. That's on the device as well. Basically everything is on the device, except for when you're trying to set the device up. Acquire some swap chain image. Update some descriptor sets. Reset the command buffer. We'll stick that next to the command buffer ones. I like sticking the ones that are related to the same sort of thing go near each other. Always a good idea. Begin command buffer. That one's that should go near the commands, I think. I don't know. I think we'll move those near, yeah. So all the ones that start with VK command will all go near each other, right? And near the command buffer one. Pipeline barrier. Bug it up. Pipeline barrier and command buffer, thank you. Next one. Queue submit. Already done that one. Queue present. Nice, so we get in very close. Basically the end now of declaring all these function pointers. Right, so now it's got to get it all compiling. So get physical device surface support. The function pointers are kind of a mess for some reason. Should we see what the actual error is when we compile it? Oh. So we haven't done vk get device proc address yet. Do we? We didn't do that. All right. So that'll be the first one that we do. Get device proc address. Yeah. Right, so that should fix a swarm of errors. Create swap chain is missed. Did we miss create swap chain? Oh, I missed all these guys. Get swap chain images, please. Create image view. Create image view. We still need to create image and everything, but that will come in a bit. And then we also need to load the function pointer for destroy semaphore. Create destroy. Destroy. Oh yeah. Right, so we've got this vk device wait idle, command dispatch, a whole bunch of these. So, so destroy swap chain, command dispatch. So that's dispatch compute shader. Command push constants and bind pipeline. Bind pipeline. Push constants. Yep. And vk get physical device surface capabilities. Right, I'm not gonna be able to type that one out, so we copy paste it. That one's a instance one, right? Because you're trying to use that to create the actual device from the physical device. Radio. Getting close. Device wait idle. Wait idle, which we should probably remove in the future. Device wait idle. And then destroy image view. Destroy image view. Huh. Incompatible function pointer conversion. Why is it different from the one in? Let's investigate that. So see these padding things. You know what? I'm not going to try and to align them. It just doesn't make any sense. Like, just put them right after. Dot star. Some of that. Yeah. So we just want to say. Bill. Next one. So an interesting one that we discovered is this one up here, this xlib one. And this creates surface. They're kind of both complaining. Too many arguments in this. So I want to like see. Oh no. Yeah, I want to go into the user include Vulkan I want to go into the Vulkan xlib at the bottom right here. So this is right. So this is the one we was calling, but now we're using the function pointer, so we're getting the type def, and the type def appears to be the same. So what did we change about our thing then for it to complain? Expected 3 but have 4. One, two, three, four. Oh my days. I hate when C compilers do this. What they do is they say, oh, this is a clear spelling mistake, so I'm going to do the compiler because I know best. I'm going to rename it for you, then assume that is correct. So rather than just stopping the errors, it tries to be helpful and produce more errors which are just wrong. So this is like classic C, right? So this is one of the things that we did in my compiler, is we basically we only show you one error because one, it's easier, and like I didn't have time to do the other one, but two, when you start displaying more than one error, is because like the rest of the code in in the C language is probably going to be wrong because you're assuming that you've fixed the error that you're fixing. Like, so it's, yeah. So that's what caught us a bit off guard for a second. So this got renamed to something else. So the reason why it couldn't find it is because we're including it too late. So include those guys for me, please, up there. So we're moving them into the header file now. That's all we're doing. Windows. And that fixes the problem. Right, so now we should only have one more thing to do. And then we should have our system up and running, and then we can start implementing resources like buffers and textures. So the issue is that HCC comes with an interop layer, meaning that we say how buffer, like unlike any other shading language, we have a sort of we basically have an opinion, and there's only one way that you should load resources, and that's fully by using using them as indices and loading them from an array of descriptors. But that's all done behind the scenes. So to make it easier, HCC comes bundled with an interop layer, which is quite nice because it effectively gives you the bindings as an enumeration for your descriptor sets. And then it gives you a setup structure you fill in with the Vulkan stuff, right? We've been over this on stream 2, on day 2. And then when you basically initialize it, and then it sets up your descriptor sets, your descriptor set layout, your descriptor pools, sets up the pipeline layout, right? And you can basically just use those now, and it's pretty cool. So the problem is, though, is the C code here doesn't take function pointers in. Instead, what it does is it takes in it expects the function prototypes to be declared. So what we want to do now is edit this and make it. So we're going to edit it here. Then we're going to take it back over to the HCC project, and then probably patch that up as well. So effectively what we want to do is find all of these in the setup code. We're just going to define a single list of all the functions that we want to call. And we just want you to get the function pointers for those and give them to us. Bearing in mind, if you don't want to do this function loading thing, you basically just assign the prototype to it. Sorry, if you don't want to load the function pointers yourself, you literally just assign the regular functions to them and it will just work. So it's not a big deal. Pipeline layout, and there's none in there. Very, very minimal. Yes, so we just need these 4 functions and we'll do the work for you. So we're just going to record a macro here quick. We're going to say pfn to get the function type name. And then jump ahead, drop that in there like that. Go down, and then do 3 of those for me, please. Voila. So all we need to do is internally now in this interop layer, cool. So now if we hit compile, it actually compiles, but the problem is those pointers will be null, right? Which means they won't actually work, it will just crash. So we just need to fix that up. So we need to find the interop setup thing, and we just need to simply, right, get these and feed them in. So we record another macro quickly, delete that, put full stop there, grab that, and then say GGPU VK, paste it in, replace that with a comma, do 3 of those please, and we're done. So we haven't actually got these in the loader yet, so we're just going to get those, go into the list of functions that we've just made. Right, these are all device ones, they need a device. Is there any descriptor set ones? Right, this descriptor set is bind. Oh, there's an update descriptor sets. We'll put it there. So record another macro, GPU VK device function. Make that all uppercase for me. And then, oh, bugger. Hopefully that's still fine. No, oh well. I tried to be a good programmer. And there we go. So that should be, now we're passing in the function pointers and it should be able to work. Right, so now what we've done is we've made a function loader to load all of our functions when we initialize the graphics, or sorry, the GPU backend. And any single time we call a Vulkan function now, it should be calling directly to the function that needs to call, as opposed to calling into this like calling into the like there's like a it calls into this library which fetches the function pointer, then it caches it in some container of some kind, and then it will do a lookup each time you do a function call. So instead we're loading it ahead of time now, and our lookup is essentially doing a read from memory, and so we've got this list here, right? In this function list, and inside this structure here we have the function list being expanded and just being thrown into that big structure. So our lookup for a function pointer now is just pulling it from that structure, which we know the direct offset into anyway. So I'll just drop the link in one more time if people are interested in reading into the specifics of that thing. But there you go. Cool, so can we actually see if this thing works? So we've written, it's probably gonna blow up. If it works first time, I am surprised. Good. So the problem, man, it's so warm. So the problem is we failed to load a function from the DLL itself, right? Oh no, we failed to actually open the DLL. Or the SO file. So this is good because it gets test our asserts out. But if we go to 36, as it was saying, oh no, it's the next. Okay, next line. Right, this one. Yeah, so this failed for some reason. I do not know why. Not load library, that's the Windows one. What are you doing, Clang? No Windows. So if the library is null, return false. If not, return true. Right, seems pretty legit. So I'm not sure if it's actually searching for so this library path here. So it's a Vulkan.so. It might have to be Vulkan-1.so. We'll have a look, but I'm sure it's in my path. We'll have a bit of a search for that. So I think it's in user lib. So usr lib, and I think we can say grep. No, find dot dash name lib. Oh, right. Sorry. I was being dumb. It's lib vulkan.so. Of course it is, right? So vulkan.1, is it lib vulkan.1? Give me a sec. Lib vulkan-1.dll. Is that what it is called on Windows? I think it's just called Vulkan-1. Yeah, I think that's it. Right. Okay. Chances are when you go and actually search for it, you figure out the name before you actually find it. So give that another compile. Give it a run. Right, so now we've got a seg fault. So, right. Here's something interesting, seg faults. Typically in seg faults, to get a backtrace, you have to go into the debugger, but it doesn't have to be that hard. Even in languages like Rust, it would do a seg fault, and it's like, well, from my last experience with it, it wouldn't give you a stack trace. So what we're going to do is we're going to break that problem. Like we're just going to get rid of this issue of having to go into a debugger, and we're actually going to print out a stack trace. I'm going to show you how to do that because I've done it in a previous project, and we're going to go fish that out. So a fun thing about it as well is you can actually do more than this. In HCC, what we've done, which is my previous project, the custom C compiler, if the compiler crashes and gives a seg fault, we write the stack trace to disk, so the user can give us that stack trace, which is really handy. So yeah, we're gonna simply steal that code. Hey there, glorious sir, how you doing? How's things going? How you been? So we're literally just gonna go into the operating system. Wait. HCC source core C. So what we want to do is find the handler, segfault handler Linux. So we're just going to have a function that's going to be called OS. In OS initialize, we'll register a segfault handler. That's what we're going to do. So in the source operating system Linux internal.h, I reckon what we want to do is have an OS Linux segfault handler. Just forward declare that like so. If that, I think we need signal.h or something. So we'll make this lovely thing, and we're going to do that in os linux.c, drop it underneath this one here. Hey there, what? Oh, Captain Chica. Right, I was trying to pronounce the CPT, and I was like, with the CH after, I was like, how is this humanly possible? But yeah, Captain Chica, how you doing? Welcome to the stream. So in the segfault handler, let's just grab this stuff. We're not going to use anything that it wants. We're simply just going to use the bstack trace thing, right? I think we'll say 2. And we're going to say core use to say to ignore the compile error for unused arguments. Where's my bstack trace at? Yeah, include bstack trace, which is the third-party library. We've got to do all that stack tracing stuff. It's only 400 lines of code. Super good. Segfault detector, please report this. See, it does it via the... right, no. It does it via the terminal. Yeah, the other applications did it via a file, because they were GUI applications. Yeah, so we should say to do output this to a file and show a message box. That'll do for now. To a file as well. I would just say also, I'll put this, just flush that out, I'm going to import, right. Then we actually want to register the segfault handler in Linux with the OS initialize. OS Linux, there we go. So we compile this and then test it out, and then we'll write the Windows version. So yeah, we essentially just use a sig action thing, say segfault, to call and use this structure to say, hey, call this handler, basically. Hey, I'm Cap Payne, welcome. Here we go, and Captain is here. Because someone took Chica and got banned. Oh. Yeah, if it's like a one word thing, people are probably going to take that. Right, so we've got a stack trace here. It's looking pretty crap, not going to lie. Have we got a corrupted stack? The names are wrong, I think. Hmm. I thought typically it would go further than that, not going to lie. Or is the segfault handler segfaulting? Hmm. Like, if it's, yeah, maybe it's recursive segfault and then it's causing it, making it a problem. I think that is the case. Because to test that theory out, we can chuck it in the debugger. BOS Linux segfault handler. Run. We hit it. Well, I think GDB takes over in that case, damn it. But yeah, we should be getting this one. Yeah, it does get really enjoyable when you don't use like when the problems that you create are mostly the problem. Yeah, sorry, the problems you solve are mostly the problems you've created and not dealing with like gluing this library with that library and then like trying to get back a result you want by like changing some parameter somewhere and hoping the system works correctly. Man, it's warm. Ooh, it's melting in my chair. Is the music still going? It better be. Let's go to a different one. Because I think we played that one already. Right, so I think we segfault in the segfault handler. Right? I think that's what happened. How could one do that? Because it's not giving us a good stack trace. Could be stack trace B segfaulting, maybe. Third party B stack trace. There's nothing you should do. Wait, where did it 362, I don't know. Oh, it's saying that. I don't know if that's right because that's in main. I don't have 362 lines, so I think it might be. I think we combine with all the same. Like, how can this be failing but not in my HCC library or application, you know? We did modify it a bit, but I doubt that's the problem. Oh, we modified the B stack trace library. The register handler, maybe that is. Is that in the main? HCC main? So the first thing we do is set up that handler. But then in the game that we're writing, right? It's basically the first thing we do as well. Here. So we set up the handler. So let's try and get another segfault to happen. Let's dereference a null pointer. Right, so this is what we want, right? Can you see the stack trace we've got? It's good. It actually goes on for a longer period of time. So maybe. See, that's super nice. And if we get a segfault now, we can just simply, you know, without going into debugger, we can just see it. The problem is, though, I don't think it always works. For some reason, it's not working for this specific segfault we're having right now. So if I try it here, what happens? Let me compile it. Right, this is a good one. Sig action in the back end, got some problems. So I think, does it crash? What about after here? Guaranteed it crashes loading these function pointers somewhere. Let's try it. Yeah, so loading some of these function pointers, it crashes. So I don't know what it is. It could be while calling into these functions, it does something which messes with something to do with the process, and then a segfault happens, and then it's unable to get the stack back, like the proper call stack. Like maybe it corrupts the call stack or something like that, right? So it will like write to the memory on the stack which is the pointer that points back to the others, like, and then so I think that's what's going on. And to solve that, I guess we just have to launch it in GDB. But hey, most of the times when that doesn't happen, I think that's fine. I mean, it's painful using OS APIs. The more layers of abstraction you add, the more headaches you receive. Yeah, that's it. Like, always dread writing code against X11 or Win32. But the thing is, when you've written it once, that stuff literally does not change. And if you want to write it slightly differently, you have the old code laying around and you can just change it. So that's what I really have come to understand, is like, it is the most stable API. Even though it's terrible, it's the most stable API you have. So you're not going to get outdated by simply yeah, it's not going to get outdated. So it's like super nice. Right, so we fail here loading these function things. Why? It's hard to tell. It is very hard to tell because it's inside of a macro. One downside of these guys, but as soon as we fix it, it's not a biggie. So I think one thing we should check is the instance actually set, right? Is the Vulkan instance set? Apparently it's set to something. So I would like to think that is, because it is zero initialized because it's a global variable. So I'd like to think loading the instance ones are fine. Sorry. I'd like to think that load with the instance pointer is fine. But what about this vk get proc? Is that just a null pointer or something like that? GPU vk get instance. Right, that's a null pointer. There we go. So we dereferenced, we called a null pointer, and then for some reason that buggered up the call stack. So this hasn't been initialized yet. So that's because, right, so I think it's trying to, this is what it's trying to do. It's trying to get the instance proc address with get instance proc address, right? We're trying to load this proc address, the function pointer, with this function pointer. So we need to actually load it from the library instead. It's a bit of a silly mistake. Then load the device proc address from the instance one. That'll do it. Let's give that a go. Ta-da! Right, we're back to where we were, but now with function pointers. So what I want to do is give that a nice commit. Oh, before we do that, let's get the stack trace. Let's get that lovely segfault handler working on Windows. Again, people who are maybe following on Windows to this, or who get the latest after I'm about to commit it, this might not compile, and I'll fix it possibly off stream, but it's probably quite easy to fix from your end as well. It's just obviously I can't compile for Windows here while I'm on the Linuxes, right? So source OS Windows. So what we want to do is go into here. So we need a OS segfault handler. Right, they use the signal thing. So on Windows, we just want to write this signal thing. So they use the Unix API, but then on Linux, they use a Linux specific API and not the Unix one for some reason, even though yeah, it's weird. Yeah, I think on Windows there is another one, but you can use the Unix API on Windows. Right, I need to forward declare this prototype because I like doing that. OS Windows segfault handler. So all we need to do is actually take that code Yeah, same code from the OS Linux one. Radio. So that should work. It does. Oh wait a minute. There we go. So use a signal function which registers a signal handler for seg fault, and then when we seg fault, we we make a stack trace, print out the stack trace into the terminal, flush it, abort, done. Beautiful. Right, so that should be the Windows side of things and the Linux side of things. Okay. Welcome, Proton Fig. How you doing? Happy Sunday to you too. It's a bloody warm one. It's bloody warm. I'm building up a bit of a sweat. Hey, Pio Trek. How you doing? Hi. How do you use debugger? Is there a great debugger inside Neovim? No. This one is a GDB front end called GF. So if you don't have a GF, I have found you one. Right. So here is GF. It's made by Next. It stands for, I guess, graphical front end or GDB front end or whatever. I'm not quite sure, but it's probably something like that. Effectively, you can clone the repo. You can literally run a simple build script, right? Next is a very similar style to me in this sense, where we just like simple ways to build things, right? It's easily themable. There's an easy theme file. You do have to know a little bit of GDB command line stuff, but there is also some graphical bits to it. So if you run GF in here, so we say dash dash args to say everything after is the arguments for the executable. And then you call the executable, and you can pass in executable specific arguments as well. And then when you're in here, if you say, for instance, put a breakpoint in GPU initialize, it will open up the window, get to the back end in it. We can then press S to step in, right? S is step in for GDB, and N is next to go to next line. And what you can do is you can see the stack trace on the right hand side. There's also other bits as well. You can click in here and set a breakpoint. You can hold Control, and you can say, "Hey, run until this line," right? But also, you can skip passcode by holding Shift and tell it to skip those lines, and don't do that, and then see how your program runs without it. So there are graphical improvements. You can also see the locals in here, I think. Well, they're not showing up for me for some reason, but yeah, there are graphical improvements to using standard GDB. And also, if you support Next on his Patreon or something like this, you can get some extra bits and bobs. If you see his GitHub, it tells you. How can I debug threads in GDB? Multi-thread programming is quite difficult to debug, especially in debuggers as well. Yeah. Because when you put a breakpoint in, sometimes the other threads are still running. No, they're not still running. Sometimes I think they pause sometimes, and I don't know, it's hard to tell. I think you have to set some settings and get it configured. I typically don't use a debugger when there's a multi-threaded problem to solve. I typically use other means. Which, I don't know, there's probably a better way to use a debugger in threads, but I don't know. Hey there, Nico, how you doing? Good day, good day. Is it warm there in Germany? Have you seen Chat Interactive AI presidential debate parody with Trump and Biden? It's so epic, beyond belief. Yeah, no, I've seen quite a few sort of chat stuff. like that. It's really funny for like comedic reasons. Yeah, it's pretty cool. Yeah, I think I've seen a Trump versus Biden one, but I've seen them like playing video games or something like that. It's really funny. Oh, there's actually a Twitch channel about it. Oh my days. Yeah, it is. It's like 30 degrees here. It's yeah, it's getting close. Just take a quick gander. Oh my days, I think I got my headphones in. Yeah, there's also like an Ask Jesus one. Have you seen the Ask Jesus channel? It's so funny. Well, I'm glad Biden can speak consistently without falling apart in that. Much better than real Biden, eh? Oh, but yeah, there's some videos on YouTube where they like play video games or something and stuff like that. It's pretty funny. About Golang, I don't know. Problem with Golang is it's like it doesn't allow you to like manage memory, and it forces you into using garbage collections. So it's just not really something I've invested time in figuring out. Like I've seen it, I've had a bit of a play, but not too much of a play, you know. Right, so let's take a let's get all of this up onto the repo. So for those who are who have access to the repo can download it and have a look or have a play with it. So we've basically moved. So we've add done DLL like that is so loud. That music. Turn that down. Add DLL loader or DLL API and load all Vulkan functions. Load all Vulkan functions from the dynamic libraries. Sorry, from the dynamic library. To avoid the Vulkan function call overhead. Nice. So let's push that up. So I've got to like, I haven't fixed this problem yet. So the way I solve it is by doing, like, I swear SSH keys worked with GitHub, but using GitLab I can't get this to work. So I've got to do this silly dance here. So that should be pushed up to the repo. If anyone wants to go and fetch that, let's get back into the fishy shell. Cool. So that was a good first half of the stream, or first part of the stream rather. What's the next thing I want to do? So we've actually changed HCC here. We've improved something. So let's quickly get that back into the HCC project. We have improved the interop layer by making it ask for function pointers instead. So we'll quickly port that over. Then we're going to do Vulkan resource loading. So we'll actually load resources. So I'm just going to go into the interop layer, drop these in, and fully overwrite them. Then what I'm going to do is go into the HCC project, and then I'm going to open up the sample program app, GPU backend Vulkan. Then what I'm going to do is find the interop setup code. And then what I'm going to do is open up the interop.h, get these things, and then simply assign the function prototypes to it, because right, we don't have the function loader in the like we've got a sample program for the shaders, and we also have a shader playground, so people can, it's like shader toy but for this shading language. So we don't have a function loader, so we can just pass in the function pointers like this, right? Playground app GPU Vulkan. So there's two platform abstractions. Let's fix those as well. So we hit F5, it should compile it all. Nice, that compiled everything. Just to prove that it worked, if I take this away, it's gonna error. Well, no, actually it won't error. It just won't, it will crash is all, it will crash. But let's go into HCC, let's get these samples, run that. The samples work now, right? I use you mean LLVM, not LLDB. LLDB is the debugger, I think. But yeah, I use Clang because the error messages are typically better, and it has more options and things like this. All right, so that's good. The playground still works as well. Oh no, it doesn't. Right, that maybe because I removed these, didn't I? And then so if I compile it again, let's prove that it works. Oh yeah, cool. So that's good. So let's quickly get that checked in. Git status. Interesting. So we've changed the interop layer. Oh, there's a shader cam there now. That's fine. That's fine. Git add dot. So what we've done is we have added. Wait a minute. We have like make HCC interop layer ask for all of the Vulkan function pointers. And use those. Git push. Right, so now that's up on the HCC repo. We can now get rid of that and get back to the game project. There you go. Cool. So what's next on the agenda for things to do? So next thing to do is sort out the GPU library. Not library, GPU subsystem. I start using that word, subsystem. Well, ho ho, I'm programming bruh. Thank you so much for the sub. Appreciate it. Appreciate it, sir. How are you doing? Welcome to the club. Let's send you a few of the lovely emotes. Thank you, sir. The Bournemouth salute is a good one. And I hope you enjoy all of the tasty content. Yeah, since you're a subscriber now, you can get access to the code by looking at the Discord and following that link. Go to that channel and you'll be able to download the code and have a play. Appreciate the support. A fellow subsystem enjoyer, of course. I love a good subsystem. Love me a good subsystem. Only good yourself. I actually have been waiting for you to stream so I can sub. Awesome. Yeah, some people like. Yeah, most people typically do that. They'll like wait for me to stream and then do a sub. Some people like sub behind the scenes, do like a ninja sub, you know, which is fine. But yeah, yeah, really appreciate it though. Thank you. Yeah. So what's next on the agenda? We've got a list. These are the things. We need to get proper sync code so we can do multiple dispatches, right? Because right now, if you take a look at the graphics, the main render function, we do a frame start and a frame submit, and then we put all of our commands in there that we're recording into the command buffer, then sending up to that GPU. So this just clears the screen using the custom clear compute shader, which we've all seen before, I'm sure, so I'm not going to bother showing that. So obviously when we run it, what we get is a cleared screen, but the cleared screen is obviously not black or white or red. It is a gradient for some reason, but yeah, that's because we programmed it that way. But if we were to do multiple dispatches, what will happen now is they will both run at the same time and they'll overwrite each other, and it will look really ugly. So what we want to do is fix that sync code at some point, but we also haven't got any resources yet. So I think before we bother doing that sync code, I think what's best is we actually implement resources properly, because right now we have this thing called a resource ID, but it isn't really anything. What it is just simply a hard-coded number, and we just assume any resource is a surface, as in the Windows surface that we render to. But what we want to do is be able to create buffers and textures that we can just pass to the shader and use. So yeah, let's take a look into how we're going to sort that one out. So firstly, we probably want to define an API. We also want to figure out what we want to support, what features we want to support, and which ones we don't want to support. So let's start with buffers because they're the simplest. And I think what we're going to say, is our so we'll have some internal things, I reckon. Wait a minute. Right, we'll slow out. Wait, how have we architected this? Yeah. So yeah, I think we don't want to. Yeah, we don't want to expose. Right. Okay, I got this now. So we have anything Vulkan is purely internal to the Vulkan compilation unit. There's not going to be any Vulkan code or types in this GPU-C. So in the internal header, which basically just declares everything in this guy, we want to, yeah. So we're gonna have to, or I've already thought of a way we're gonna solve this now, but I'll talk about it when we get there. So we have to find a way to sort of, where are we going to store the internal, like the back-end data, like the VK, like the VK buffer, where are we going to store that, even though we're going to have a public, sorry, a structure which doesn't quite have access to that type, right? And doesn't quite know the different shapes of the backends, because they're all slightly different and some require more fields than others. So basically, each buffer, texture, and maybe sampler, I think we'll leave samplers out until we need them. But we're going to have a thing called a resource. And that is going to be a buffer or a texture. And you're going to be able to pass this around as an ID. And this is an internal structure that represents it. So what we're going to do is have this ID. Now, this ID is what gets passed around. So we need a way to create so we'll have a GPU buffer initialize, and you'll get back a resource ID. And we'll have some arguments here. You also have a texture one as well. And then anything else would be like, that's to do with a resource. Yeah. So what things do you need to initialize a buffer? Let's start with let's start with this. So you have a buffer setup. No, spec. Wait, create info. So you have this create info. So what arguments are kind of something we need to think about in our abstraction? So we need a size of a buffer. So we need to be able to say. So we need a size. We need a usage. Do we need a usage? So usage, we basically, when we create a buffer, we're only, like, this is, I think these usage flags are only useful if you use the full extent of the Vulkan API, but what we're trying to use is a minimal set of the API, right? We only care about it for compute shaders, right? And we don't use uniform buffers, right? So basically all of this is useless. The only things that we need to figure out is transfer source and destination. But to be honest, I think all the things that we use transfer source, like an upload buffer, is going to be implemented entirely by the backend anyway. So I think we can keep our system insanely simple and not care about usage, and assume it's always got transfer destination depending on the memory locate. Or no, I think we'll say all of any buffers that are created using this API are always only on the GPU. There's never one that's CPU visible. That's always CPU visible, like you would an upload buffer. Yeah. So that means this usage flag is entirely pointless for this API, which is good, because that completely eliminates an argument. So if you make your buffer type very flexible, you'll need a usage flag. And one prime example of this, if you were to see another API like a web GPU. So if you look at web GPU, if you look at their buffer creation, right, they have a buffer descriptor, that's their create info. They have a usage flag, but but they don't have as many, right? But that's because they're exposing it at more of a lower level rather than trying to bake that into the API itself by having different constructs. They give you more of this flexible thing, right? So but the way we're going to design this API would be more higher level, where we have a specific uploading API, and behind the scenes it will create an upload buffer where we temporarily write into that, and then it will copy it on the next frame of the GPU. So yeah, these are things to be aware about. Is how can we remove fields and things like this? This should work even if it's not the fastest solution. It's good to start with the smallest possible subset if you're only doing compute. I doubt it's fast enough, at least. I doubt it's not fast enough, at least for now. Yeah, I think metal typically is nicer to use, isn't it? And I've not used D3D11, but yeah, I know what you mean though. It's typically the right level of abstraction. But yeah, that usage flag is quite, like, the buffer is made to be extremely flexible, and if you break it into its separate concepts, if you will, very overloaded term nowadays, you can implement it in a few different ways in a very specialized way, and then it gets rid of that flexibility part, which is really nice. Right, so all we need is a size, basically. All these create flags. None of this crap, because that's all extensions for specific things. Sharing mode, don't care about that. Don't care about the rest, right. So to create a buffer, all we really need is simply how big it is. So buffers in, we'll do a U60, we'll do a U64, okay? I'm not, like, typically you don't want to use over 4 gigs of GPU memory. Sometimes it's very difficult to, but GPUs are getting loads and loads of memory, so I'm going to future-proof this. Just use a U64, I think it's fine. You could maybe go over U32, but I don't think changing it to U32 really gives us any benefits, to be fair. So let's just use U64. So that's actually, like, insane. We can just shrink it down to that. One thing I would be but another thing that is useful is also a name, right? Can I get a name or something, right? So when we're debugging this and I have this resource, can I get a debug name that will compile out? It's like right between OpenGL and Vulkan. It's enough control where you're not writing low level driver either. Yeah. Yeah, there's so much like specific code you have to write for Vulkan, it does get really insane. I miss triangles, but Perry, we got squares. We got rectangles, Perry. I hope you like my rectangles, Perry. But Perry is 2 triangles. Well, it's not 2 triangles, I'm lying. This is Manjaro Linux. And yeah, using U64 is good on a 64-bit system, I guess. But you should use U pointer or like a size T. But on GPU, it's difficult to tell. Oh yes, I love that quote. So one thing to keep note is we haven't really defined what is this GPU resource ID, right? So before we go and write the texture one, So now we've simplified this down heavily. What is this GPU resource ID? So in the past, you may have heard me speak about maybe having an object pool. This is something we can do. Or like if people are not familiar with like an object pool, it's basically like a slot map. It's like an array where you can have holes in the array that you can deallocate, or you can like allocate individual slots in the array and then deallocate them individually. It's super fast and super awesome. It's really great. But that is something that sits on top of an array, right? The most simplest thing you can do is an array, right? Is using an array. What the object pool gets you is it gets you tracking where if you refer to something as a resource with this resource ID, which is just some integer, essentially it has some extra tracking bit, or it has some extra bits in the top which basically count the generation, or like the so if you were to free and then reuse the same slot in the array again, it will up the counter and store it in the handle, so you can track for use after freeze, or if you're freeing the same resource twice. So we can go ahead and do that. That is one method, but you can also get away with just using arrays if your resources are known at compile time and static, right? Because then basically you just initialize all of your resources, and then you can just refer to them basically as an enum. Now, as much as this idea is interesting, so I could say like GPU res ID, I don't know, I could say like surface. There's our surface resource, and you can just refer to them like this, and then I can remove the whole idea of this ID. And they're just hard coded, right? So anytime I want to add a new resource, and since it's my own code base completely from scratch, it doesn't matter if I simply just add a new enum here. I can just add a new enum and then the resource can get created. But there is still going to be a case where it can be freed then allocated again, right? So maybe an object pool is just the thing to do, right? Like also another benefit of having this enum known at compile time is I could share this with my shaders, and it means that we could basically don't have to pass these resource IDs into the shader via push constants. We can refer to them statically and compile the index, like the bindless index, into the shader. So it's very powerful way of doing it. But the only downside is as well is if you load any resources dynamically, say if you add the ability for people to mod the game, you either have to have like texture atlases that basically texture like atlases where you sub allocate a texture from it, or like you have to like pre-allocate like ranges of things and only load a single part of a mod at a time or something, you know what I mean? Like, and like, so it does get, it's very powerful, but at the same time, like, if you're designing a specific game that doesn't need to be flexible, it's quite a good thing. But I think for this project, I want to just simply do the dynamic approach, because it's not too much extra work, and we're going to be needing an object pool anyway, right? So I think before we start implementing this, we'll quickly write an object pool, and then we'll we'll write this API, we'll implement the API. But first I want to implement the API, then we'll write this object pool and then get going with that one. Oh, wait, what do you mean King Theo? What? Did the stream... Well, I think it's good my end. It might be your end, I guess. Hey there, Thermi Soil. Do you use CI/CD pipelines in your job? Yeah, like they're pretty much standard if you work in a team. Wait, why have I got this web GPU thing open? Close that. Close that. Yeah, we like typically in if you work with groups of people, you want to make sure that like someone else doesn't break someone else's thing. So, or you know, people don't stop groups of people from like imagine if someone commits something to the code base and then it stops like 5 people from working. Like you typically want to try and minimize that as much as possible. So you kind of put like a thing so it makes the person who's committing to the code base make sure that their code actually compiles, right? So yeah, like having that stuff is basically vital working in teams. Awesome, good to hear, guys. Good to hear. You know what? Why haven't I given Nico a sword yet? Wait, let's make sure we don't get the robot, because that could be very dangerous. Imagine if we get... Right, there you go. Enjoy the sword. Welcome to the mob group. Good, very good. So one other benefit over this enum approach is we can declare an enumeration, we'll lookup table for the name, and then the name is, rather than being passed up every time we initialize the thing, the name is passed, like it's just in some lookup table. But yeah, like pros and cons. So anyway, I do like the debug name thing. It's super nice. We're gonna write the word debug names to specifically say compiled out when the game, you know, is in release mode or something. So one last API is to initialize a texture. How does one make a texture? So I guess the other one is like you want to be able to like resource DNet. Res ID, I think we'll call it. Should we shorten it to res ID? Like typing resource is just so long, you know? It's way too long. So let's just do that. And we'll say, rather than resource, we'll say res, okay? So this is cool, I guess. But then res, you know, we're going to use the full name resource because when people say res, sometimes they mean like result. But yeah, I think we'll keep res ID for short there. I think that's good. So, right, what are the parameters for this thing? So now we're going to go to the texture. So the texture is actually a piece of work. It's called image in Vulkan, which is not really a favorite name by the community because I ran a poll on my Twitter once. See if I can find it. Right. What do you prefer, graphics APIs and shaders? Texture or image? With 23 votes, it was a 95% win for texture. So not many people apparently like the word image. Because texture is just ingrained in people, I guess, now. So, anyway. Oh, resolution as well. Yes, another one. Yeah, very, very overloaded thing there, isn't it? By the way, I found some data erase bug in HTC while pointing it to FreeBSD. Oh no. Hmm. Probably all my silly atomics. But then again, I do run it in. I run it in single threaded mode by default because I basically implemented the multi-threaded thing, realized it was slower, and then I couldn't be bothered to go ahead and make it faster because it was too much of a fun, it was too much of a fun thing rather than a get stuff done thing. So I put it on the back burner. But yeah, where did you find it? Like, did you try running the multi-threaded stuff, or is it? Yeah, so did you try running the multi-threaded stuff? Or like technically there is thread still. Like you have a when you make a task and then you dispatch that on another thread, but the other one waits. So maybe there is a so while the compiler's running, this one's waiting. And then when the compiler's finished, it gives this one back control. Right. So maybe there's a data race there. Um the compile X is without doing anything. Oh. Yeah, see, it launches another thread to run the compiler, so I guess it's not waiting. Maybe. Right. So images. So what do we need from the image here? So there are different types of images, right? There's image 2D, image 3D, image 2D array. There's all of that stuff. There's formats. There's an extent. There's all sorts of things. So let's get the texture type. So type def. So this is not really the best way of defining an enum, but oh well. It doesn't make it type safe, but then it means that you can actually define the size of it. I think in C23 you can define the size, but anyway, this is the way we roll. So 1D texture, I don't know if we'll ever have these, but let's put them in anyway. As you know. I don't think we're ever going to use them, so let's not put them in. 2D arrays are useful. And 3D. Right? There's also cube maps. I don't know if we're going to use cube maps. So I think this is all we're going to need. So we need a texture type. That's good. We also need a format enumeration. So we're specifically going to call it a texture format. So the reason why it's called format in Vulkan and called maybe DX format or whatever it is in DirectX is because it's more than just a texture format, because they actually use it for the vertex attributes, but we didn't have vertex attributes because we don't have vertex buffers. So yeah, this is actually really long. So let's not call it texture format. Okay, let's just call it format. GPU format 888. Do we want to do R8G8 bit? Because sometimes it doesn't work out. RGB. Yeah, let's say RGB. Right, I think let's do A. Yeah, but then it doesn't. Yeah, we'll put the separators in RGBA. Alright. So I think we'll just start with that one. We'll add more as we need them. So we're also going to add a count at the bottom. So this allows us to make lookup tables and to iterate over them by having a count at the bottom. So there's our format. This defines like a texture format. So this is basically saying like a standard color, 32-bit per pixel, 8 bits per channel, RGBA. So you can have other ones. Obviously, there's sRGB, stuff like that. So by default, it's linear sRGB. Extent, that's another one. See, there's quite a bit. There's MIP levels, array layers. We're not doing multi-sample. So because there's so many parameters, we might do a setup structure, but let's just see for a second. So let's write them all in. Texture type. So what's the type of the texture? Format. U32 times 3 extent. Right, what is the size of the, or dims maybe, what are the dimensions of the texture? MIP levels. Array layers. Multi-sample, no. Tiling. So where's tiling? So tiling is saying optimal or linear. So you're either saying we want, like, if you map the texture into, like, if your texture is CPU visible and you map the address and you write to the texture directly, you want it in linear. But since these are only going to be available on the GPU, you want them in optimal. So one more formats are supported in shaders, like in shaders basically, and 2 is faster because it's stored in a specific format depending on the layout of the image. Like, is it being read from, is it being written to, that sort of thing. Awesome, thank you, Nico, for the importing. Almost looks like a Vulkan abstraction library now. I guess that's the point. Yeah, because like, how else are you gonna do graphics across, like, across platform without writing specifically Vulkan code and Vulkan helper code? Like, the best way to do it is to abstract it. So the issue is though is, I'm so sorry, but the best thing is though is this is probably going to be one of the simplest like APIs, right? Because we're essentially getting rid of all the stuff we don't need and making it work in a different way, right? So I don't think we need anything else. You can alias textures, but we don't need that yet, so there's no point. There is usage as well, but we don't need that as well. So yeah, this is looking good. So the problem is this is a lot of parameters. In general, my rule is 5. Oh, it's a bit of dirt on my screen. It looks like a semicolon. I've got a bit of dirt right where the comma is. Okay. Typically my rule is 5 parameters. But hopefully these are distinct enough to the point where it's understandable. There's 6, right? So if you go any more, I typically either want to, yeah, typically make a setup structure, but I think this is fine. Okay. So this is great. Um, so if it's a buffer, so we'll say texture. So there is also like texel buffers and stuff like that, but we're not going to use texel buffers. Yeah, so there's that one. Alrighty, so the debug name goes at the top, is across all of them. If it's a texture, we'll have these guys. If it's a buffer, this is just going to be garbage, probably just 0. And this is the internal resource behind the scenes. Then the backend stuff, what I'm thinking of doing is leaving the bottom part of it, right, to be the backend stuff. We could store it in separate pools. We can store in separate pools, but the issue with that is it means we have to have separate pools, right? And it's just effort. It's just more effort. Or is it? It would just be an array you create where you can index the array and just get the data, as opposed to doing a cast from the pointer. Yeah, so I think we're gonna have a... Yeah, because the other route I'm thinking is you basically just have like the backend data here, and you have to have a size of the data. So maybe it's like 24 bytes or something like that. And maybe this changes for each platform, and then it's stored directly in here. Or the other way is to do a look it up in an array in each backend every time you want to use it. Yeah. I'm not sure what's best, because when you use the backend code, the backend handles like the VK buffer or VK image. They are typically... In debug code, you will use both of them for assertions. But then in release code, you might just be using the raw handles most of the time. But only when you create stuff do you use this data up here. So I think it might benefit, providing there's not too many holes in the arrays, like with empty slots, maybe having a separate array for the backend data, I think. And that way we don't have to worry about maintaining this size of this thing. So let's try that for this project. All right. So this, I guess, will stick around here for debug, maybe. Yeah, for debugging. Maybe it can be compiled out, which would be interesting. Right. So I think that's pretty decent. So before we can continue, we do need a way to actually allocate and deallocate these things. We could go ahead and implement them. Right. And avoid... We could, in a very, very simple way, implement this now, and then do the object pull after. Yeah, let's implement these since we're in the role of designing this. Let's actually get this done rather than implementing an object pool. We can easily swap it around later. Okay. So internally what we want is a way to get this structure using GPU resource get using a GPU resource ID. So we'll implement that internally as well. So we're starting to get to the point now where we should probably start putting stuff into sections of things. So I typically like where's my okay, I'll go into the oh, it's so bloody warm in here. Might go and get another cold drink in a bit. Resource. So I think we're getting to that point now. So this is to do with resources. This one is to do with this is the actual subsystem. Then we obviously want to have the sort of commands section. Awesome. So this is the public interface, and then there's an internal interface. Yep. And then we implement that inside. So we don't have any globals yet. You know, every good project needs a good set of globals. So we're going to go ahead and do that. So we don't have a GGPU yet. So we have GGPU Vulkan, but not GGPU. So simply, we are going to have an array of resources. We'll say extern, because we'll define it properly later. So right now, we want to make this an object pool later, but right now we're not going to do the checking. Resource pool or resources pool? Anyway, to do make object pool when we have one. So for now, we're just going to say, hey, there is 32 of these guys. And we are simply going to just bump allocate them. And yeah, in the future it'll be done better. All right, so let's get going. So we just need to probably shuffle around this a little bit. Let's bring the headers in. This GPU one. Then we've got commands one. How's the camera? Is the sun breaking through yet? Oh, good. Drop the commands in there. Oh. Ah, you bastard. Right. Cool. So let's get this rolling. So these are lovelies. So we want to have like a U32 resource. Oh, wait a minute. Oh, yeah. Next ID. So the next ID is actually going to be 2. And it's going to be static. So we say ID equals basically, right, next ID. And then we say to do allocate using object pool when we have one. And then we will return the ID. Now what we need to do is actually initialize. We need to actually initialize this thing. So So how can we tell if this thing has been allocated or not? Well, how we tell that is if, like using the object pool, that will tell us. So for now, we're just going to skip out on it because we are literally going to replace it in the very soon immediate future, right? So we just need to initialize this, right? So after we've allocated it, we can do a get, and that should return a pointer. Don't let that fool you. So we call this the res. Use the res ID. Get ourselves a res. So we don't have a type in here, which is a shame. So telling whether it is a buffer or a texture is not easy. Instead, we'll probably call this resource type and then ban you using buffer as when it's texture, right? Buffer, and then if there's only one type of buffer, then it's just texture. So now this will actually stay in there, probably go at the top, right? Hey there, Marco. How you doing? Welcome. Oh. Actually, thinking about it, if we have a type and it can be a buffer or a texture, then if we need to fetch, in the back end, if we need to tell whether it's we'll need to always know both structures anyway. So storing the backend data separately might get buggered up then. Yeah, I don't think storing them separately is a good idea. I think that's a good idea. I think the backend data should be bundled in with the structure because it'll be a good idea. So I think a lot of this, yeah. So I think we should have a UA. So we should be able to say like, I think we'll do a static assert. Can we do a size of? Yeah, we can. Good. So we'll say like if defined OS, core OS Linux LF Windows I guess we have an else as well and just say unsupported platform. Sorry, error. So here we want to define a GPU resource backend size. So on Linux, I think it's going to be like, I think you need like maybe 3 pointers. I think. Let's see. There's some distracting material. Oh boy. On Windows, I don't know. Oh, Windows would be the same thing, wouldn't it? Like, so we don't really have if defs for if we're in Vulkan or not, right? Do we? Interesting. So really like hmm. So maybe in GPUH, maybe if we say if you're on Linux or Windows, define GPU VK. Right, and then we use that as the ifdef. Yeah. Ta-da. So then we're going to have this backend data, which we're going to cast into a proper pointer, and it's just an array, like an array of data, which we'll cast into a pointer, and we'll check it in the backend to make sure it's what we expect. So we'll get to that in a bit. Here's some distracting material. Oh boy, let's take a gander. Red sanitizer data erase. Oh. Semaphore initialize. Oh, it's okay. Right. Take or wait. Interesting. So it's in the semaphore. Hmm. Did you implement take or wait? Like, because it was using Futex. Did you? Is there a Futex in FreeBSD? How did you implement that? Right. I see. Right. Yeah, probably is a bug in that then. Right. System V semaphores. Right. I see. Yeah, because I wanted some custom ways of adding. Yeah, using semaphores that because classic semaphores are very restrictive. Like you can't add to the integer. But yeah, it's that wake up logic. I see. Oh. Then sometime later. Right, so then you run HCC, do a good old compile. Right, so you simply didn't initialize. Was that the problem? They weren't initialized? Oh. Oh, am I? Oh, interesting. Right, thanks for finding that. So that's the problem. Uh, yes. Programming. Right, so we need to add a getter as well. Let's get the getter in there. I think we'll put the public ones on top, the internal ones at the bottom. Well, that's one problem. Still doesn't do anything. Oh no. Layers of problems on problems. Right, so after we get the res, yeah. So we're gonna set, so for a buffer, we're gonna say res type equals GPU resource type buffer, right? And then res debug name. We also need to size properly. Wait, does a buffer, sorry, does the text want a size? It's purely on GPU memory, so you probably don't need a size there, I think. So I think I might union this. U64 size with a buffer. Yeah. Cool. And then we simply set res buffer size equal size. So we have to make sure we put an assertion in here. So we're going to say core assert size, and you say size cannot be 0. Ta-da! Gonna scream it out of their face. So after we get the next ID, we need to also increment the next ID. Again, not the solution we're going with in the long run. We're just avoiding writing an object pool now. We just want to get resources working. Right, then we need to call into the backend. So after we've set this up, we need to say backend buffer initialize. And now what we're going to do is pass in the resource, okay? And then it will initialize a buffer, set the backend data in that backend data section, and then return. If it fails, it's going to crash, I guess, in the... cool. So we obviously need to define that. We'll define that later. No biggie. So let's get the texture one written up, and then we'll do the other ones as well. So basically texture so type must not equal to GPU resource type buffer. Type must be a texture type. I think we're going to have an undefined format, I think. We have an undefined format. Do we need an undefined format? Maybe, we'll see. Wait, do we need an undefined format for some reason? So you just use it on the textures. No, I don't think we need one in this code base. Dims, so we need to assert that each dimension, dimx. So we just want to say, I think, all G. Do we not have the maths library in here? Include hmaths generics. hmaths vector. There we go. Isn't that beautiful? Texture type is actually resource type. So we're just basically saying we expect that all of these are not 0. That's all does. It just, and there's any as well. MIP levels. Dims must not have a 0 element. Yeah, let's not put the exclamation mark there. Right. Then this one is saying MIP levels cannot be 0, same with array layers. You see, we might have a texture initialize, like a shorthand version, because I doubt we need MIPs or array layers much. But we can just do 1, 1 at the end. Yeah, I don't think it's not bad. We could do like have an EX version, right? Like an extra version. I don't know. I think that's fine. Okay. Right. So what's next? So now we need to actually set all the parameters up. So you set type in there. Now you say texture. So it's texture format, dims, right? All the things we had. So just copy paste that 3 times. Format, dims, MIP levels, and array layers. Okay, now we go into the back end and we initialize the object. For a texture, like so. Right, a couple more. So we're going to do an abort here. Call abort. To do implement when we have an object pool. Okay, very nice. So this surface resource ID, this one's not going to be hard coded. So I want to say like to do when we have an object pool, make this in GPU initialize, right? And store as a global. To be honest, I could just store it as a global right away, right? I could just be like GPU resource ID, and we're going to say, hey, this is the surface resource ID, because that's how it is going to be. This is going to return GPU surface resource. Let's do res ID. So this hard-coded index, get rid of that. So we'll take this down at the bottom of here. Let the backend initialize, and we're going to say GPU. No. Surface res ID dot raw equal 1. We have an object pool, like allocate it from there instead. Ta-da. Right. There we go. So here's the front end interface now. So now what I want to do is implement the back end and go through and implement that in Vulkan. So I remember actually another thing Zaka said like earlier in the chat, almost looks like a Vulkan abstraction library now. I guess that's the point. Another thing to add to that point that he made is that actually the Vulkan library is the Vulkan backend is the Vulkan drivers are typically, from what I understand, is they actually don't track anything. Like the whole point of Vulkan is that it's explicit, meaning you pass in everything, and the driver kind of remembers. The driver has a very little logic as possible. Like it obviously creates internal state, but that internal state is very minimized. So I don't think that the Vulkan drivers typically will have, like it could do, but I don't think it will have like the size of the buffer and everything in the driver unless it absolutely has to. Like I think it can omit a lot of this. And when you create the Vulkan image, you say the number of MIP levels and array layers, and all the driver does is it just allocates the memory for that, and then that memory is just an opaque data pointer that it keeps hold of. And when you in the future, whenever you refer to any of this stuff, you look for array layers. Throughout the code base, whenever you refer to anything via this sub-resource thing, right, you have this, so like I refer to I've buggered up this, innit? Yeah. No. Yep, fixed it. Good. Right. We're good? So if I knock my cable, sometimes it does that. It disconnects and connects again, and OBS panics. So anyway, back to here. VK image sub-resource. So you're referring to specific MIP level or a specific array layer. Maybe it keeps hold of some information. But yeah, I think typically the Vulkan drivers try and be quite slim. I think it's sometimes called layer. Layers. As well. It's hard to tell. Yeah, no, but yeah, they have specific offset. Yeah, I don't know. Yeah, so I don't know, I've not really written a driver, but I think a lot of the time the drivers stay slim. And then on top of Vulkan, what they do is they have the Vulkan validation layers, and those things implement the tracking logic on top of the driver. But it wouldn't surprise me if they do track some state, because they have to. But yeah, anyways. Back to carrying on and getting this thing implemented. So one more function left, right, is this one. And again, it has another to do, right? So to do, when we have an object pool, get it from there instead, and obviously it will do it will actually do the assertions properly. So for now, we simply want to return GPU resources pool res ID. I think we're going to take away 1 because 0 is null. Yeah, I think that's where we're going to roll. Cool. So that is a good one. So a lot of this, all these errors now are simply from not implementing the back-end side of things. So let's go and do that. So we need to go into GPU backend.h. This just defines our backend interface for this just defines our backend interface, which is only included by the backends themselves. So we're just going to go ahead and do that one. So we want to pass in the resource structure, which has all the data. We don't necessarily need the, I'm going to use the full word resource for these. We don't, we don't typically need the resource ID, but I guess we want an internal function to say get ID, which does the other way around, right? So that would be really nice. It basically just, if you have the points, you can get the ID back, because sometimes that's useful, but not all the time. So we won't bother passing it down all of the time. Just to keep the number of parameters simple. So let's just quickly implement that one. So again, to do, we will use the object pool function for this. But for now, we'll just take away the pointers. So it's just an array. So you just do a pointer difference. Sorry, pointer subtraction. And jobs are good. Then it's +1. Because that's 0 based, when it be 1 based. Do you use bullet physics to see you write games and see? I use bullet. And says, what do you mean by bullet is COP? I've not written a game yet, so in terms of what I do for physics, it would probably be a custom physics, right? Because 1, it's interesting to learn, and 2, hopefully we can just do something simple, right? It's always good knowing what other people do. I'll see PP. Yeah, I typically don't use libraries because I like to understand things. I typically just write against the operating system, I've written my own custom physics before. Not anything super amazing and super awesome, like I haven't done GJK, right? But I've done the other approach, right? Is IK simple? Inverse kinematics. So what you're saying is like, I move my hand here, and therefore I'm going to move the rest of these joints, right? I pull this bone, there, it moves my wrist, right? That's inverse kinematics. So IK is like, you're basically like, if you can render I think it's simple, right? If you know how to render an animated mesh, the maths is pretty much this. Using the same mathematical concepts, like, uh, yeah, you're using the same concepts, just um, obviously implemented differently, right? So if you can render it, then it's the same set of skills. But yeah, is it hard? Or is it simple? Once you understand the method behind it, it's relatively simple. Yeah. Yeah, that's what I think as well, yeah. Yeah, I think that's right. Scallywag. Welcome, Scallywag Software, welcome back. Yeah. Yeah, that's right, that's right. Backend initialize. Backend DNA. How's things been Scallywag? And also welcome back, Kappa. How you been? Cool. So we're in the back end now. Perry, watch out. Um, yes, this one's going to be a to-do. Let's just get this right. This one is going to be an abort. I'll do you later. Implement when we have an object pool. Exactly. So these ones, this is where the fun begins. We're actually going to do some Vulkan code now. Insane. Yeah. So we ultimately need to call vk create buffer. I'm going to start with the buffer because it is the simple one. vk create buffer. Here's your boy. Pretty good, just goofing around with some noise functions for Moja. Cool. Yeah, I've had a bit of a play with procedural generation. It is fun. It's something I do want to explore more. Like I did like an island, for instance, like an island on a texture, and just did a height map, and then got the terrain in 3D out of voxels, but it didn't look anything special. Like it was pretty lame, to be fair, but it was interesting to learn about it. Something I'll probably want to dive into in the future, but we'll see where this game goes. In my engine, I load from OBJ files directly, no idea how to start animating it. My character is Steve, made of 6 boxes. Yeah. You should take a look at the GLTF format. Because you can basically export from Blender or Maya or whatever, get an animated mesh from there, export it into GLTF, and then load it in. It's basically a Chronos standard, right? It's pretty okay. But there's a single header library you can get that works in C. There's Tiny GLTF, which is a C++ one, and there's I'll just send you the Google link. Actually, maybe that's not a good idea. Yeah, there's Tiny GLTF and there's C GLTF. Take a look at those, and you'll be able to open up a model and get all the animation data for all the bones and stuff like that. But yeah, and then I guess do some Googling to try and figure out how to actually get that rendered. But yeah, what sort of you're saying you're goofing around. Have you got any projects you're gonna be building with those noise functions, or are you just having to play and see how it goes? Yeah, we've got Voxel Engineering getting into starting on biomes. It's fun because low priority, effort, high reward. Oh, okay, I guess you're answering the question. Ah, yeah, yeah. Yeah, that's very cool. Yeah, yeah. It's fun doing a voxel thing. Like, I wouldn't want to do a voxel game, but experiment with voxels is fun. Like, I wanted to do voxels a couple of years back, and then by the time got around to doing it, there was already people doing like the voxel stuff was coming back in. Um, like when Minecraft came out, it was like voxels are like very like people loved it, and then it started going down again, and I was like, I should probably be interested in doing a voxel thing, and then it like went back up again. So I want to try and do something different other than voxels. But yeah, so I've got this VK create buffer. So typically VK create works. The function prototype is basically the same. You pass in the device first, then you pass in the create info, then you pass in the allocator callbacks, and then you pass in the buffer that you'll get back, and then it always returns a VK result. Now, the allocator, by the way, is not how you allocate the buffer. It's how the driver allocates its memory to handle creating a buffer. It's just Vulkan. It's silly. But yeah, typically you pass in the same allocator all the time. I don't know why they just didn't set it into some global thing, but anyway. So, well, I guess you might want to change it in some cases, and it's a general API, so they've done that. But have we got a to-do custom allocator yet? Damn it, we passed in null? That's not good. That is not good. Alright, we'll fix that. At the top, we're going to say to do GPU VK, oh no, to do GPU VK allocator. So we'll say like to do when we have static, or when we have custom allocators, implement these. So I'm looking for null specifically. Some of these, that's that one. Because we will get quite a lot of these, so it's just good to cover your bases here. Create semaphore, create module. So when we have custom allocators, we'll swing by and patch all those guys, There you go. Good. So let's get back to that create or like buffer initialize, shall we? So with buffer, so we got this VK create buffer. Remember, there's that big old, right. So at the end, we're simply going to say GPU VK assert. So you put the expression in here. We need to have a VK result on the stack, because behind the scenes it simply sets this, like in this macro it will set that local variable, and then it's gonna test the local variable, set the local variable, test it's a success, and if it's not a success it will print out a string of that result in an assert message right? With a stack trace and everything. So it's super nice. GPU VK dot device. We need the create info, which we'll fill in just a minute. We'll need the to-do allocator, which we'll fill in a bit. Then in the resource, we need the backend data for this. So I think what we want to do in the internals, we want a super lovely function to say, hey, VK resource backend, right? Find me a backend. VK resource backend. I'll say VK resource. Oh, not really sure about the name. I could just call it backend. Or VK resource. Yeah, I'm not sure. I'm gonna call it backend. Yeah, it's better. Yeah, I'm trying to do something different than Minecraft for sure. I don't use anyone else building. Sorry. Let me read that again. I don't see anyone else building the type of game this engine is working towards. Check in with me again in another 5 years and I'll tell you how it went. Sweet. Yeah, I'll keep asking you. Don't you worry. But yeah, typically you do like small voxels, or maybe you render the voxels differently. Maybe you curve them, or you know what I mean. There's things you can add where you're just not copying people, which I think is great. Right, so this one's gonna say VK buffer, but there's gonna be more bits in here, guys. We also need VK device memory. What is this? Ooh. What is... And also, like, we might need some other things. So you need to allocate your memory manually on the GPU in Vulkan. How does one do this? Well, we'll save it for later. For now, what we're going to do is simply get the backend, resource backend. So we probably want to implement that guy quick, not too hard, right? I think we want to do it properly. So we're just going to have a pointer. I don't think we need to bounds check it really. Should be pretty safe. So we should be able to just say, oh crap. Resource backends, all of the backends. So we need to allocate that properly. Get to that in a bit. Bottom down here. We're simply going to return the... Oh, wait, no, sorry. We're not allocating an array of these anymore. Remember, we're storing it directly in this structure, aren't we? We're storing it directly in here. Okay. So we might not need a function anymore. But maybe it's good to make a function so we can change it later, but I doubt we'll change it. Return the casted version of the resource backend data. Right, it's what it's going to do. Then where we define where we define this, we want to do an assertion, static assert. So we're going to go to static assert, source call h. C static assert header. It gets deprecated in C23. Assert.h. Ugh. Don't want to include assert.h. On Windows, it's already defined. Static assert keyword. There you go. I'll do it. Okay. So static assert needs a. We want to make sure the size of this is equal to this backend size. So we want to say like must be equal to no. Ta-da! Alright, so it's obviously wrong at the moment, but we'll fix it when we actually get this thing compiling. We'll go fix it. So that's super nice. So what is something? Wait a minute, we're going back to. Source GPU backend Vulkan. We're going to create a buffer now. Remember, back on the buffers again. So, back to where we actually were. Backend VK buffer. So that creates a buffer. If it fails, it will crash with an assert. It's asserted basically with the VK result, and it'll give us a stack trace. Now we need to actually create the info. VK buffer create info. And so we need to set the S type, standard Vulkan stuff, structure type, buffer create info. P next is null because we don't have any extensions. Flags is probably null. We'll look into that one. Yeah, none of these guys are all kind of extension-y thingies. So 0 for that. Size is going to be equal to resource buffer size. Right, super nice. Usage flags, hard-coded. So for this one, the usage flags need to be, so this is GPU only, so potentially it could be uploaded to, so it could be a source, transfer destination. Yeah, it could be a transfer destination. And it also could be, no, it is going to be a storage buffer, right? None of the rest of these. So that's that one. Then the next one is use sharing mode. So exclusive or yeah, I want to use exclusive. So there's exclusive or concurrent. It basically means if you have multiple queues that you submit down and the resource is used across multiple queues, do you want it to be exclusive to one queue at a time and you transition it? Or is it concurrent? We only have one queue, so we're just gonna be... No, I think we'll say concurrent, because it's easier. Yeah, and I don't know about the penalty about it, to be honest. Because we might have a transfer. We'll have a transfer queue in the future. And the transfer queue obviously would be different, and you'd have to transition it manually. If you have transition code anyway. Maybe... So you transition it manually and then put it back. And maybe you have multiple compute queues for reasons. So I don't know. Yeah, no, I would say concurrent because it'll be easier. So if you say exclusive, you need to specify your queues in here that it'll be used down. But we don't have any, so we just do that. Right. That's looking pretty good. We need to say GPU VK to use the function pointer instead of the function. So create buffer is not in there, so we need to add it to our new lovely X macro list of functions which we added today. So this is a device one. So it'll go next to the image ones. Oh crap. Like so. There we go. So when you create a buffer here, you might think, hey, this is awesome. We've made a buffer now in Vulkan. Well, we still need to give it memory because in Vulkan, it doesn't come with memory. So the function you need to call to bind the memory, so this is the easiest thing. Bind buffer memory. There's a bind buffer memory 2. I think we'll use that one. Because it can have extensions, you might have dedicated. Yeah, we'll use it. This is probably the better one to use. Bind buffer memory 2. It's a little bit more complicated. It allows you to do multiple binds, but whatever. So we'll have to fill this thing in. Returns are another result. Bind buffer memory 2 GPU VK.Vulkan device. Pass in 1 and then address of bind info. Cool. We'll make this super lovely structure, call it bind info. And the plan is to set the S type. S type is VK structure type. Bind buffer memory info. Pnext obviously null. The buffer is the one we've just made, so resource backend buffer VK buffer, right? Remember we got the out pointer here, so when it gets created it goes into there. The memory. We do not have the memory. Ah, that's a good question. Do you ray trace or use meshes? Mm-hmm. Oh. So memory, we don't have the memory yet. We haven't made it yet, but I'm just skipping ahead just to show why we need it and how we're going to use it. Memory offset, we're going to say 0 for now, but we'll say memory offset. We'll put into a local. So this needs to get saved, and voila, we have done it. So U64 memory offset. And there we go. So what is it like to allocate memory in Vulkan? And how do we do it? So it's actually a very silly and painful thing in Vulkan. Like DirectX and Metal basically have the same sort of API. In Vulkan, it's very opaque and not very transparent, right? So in Metal and DirectX is quite transparent in a way, where you can sort of see where the memory is allocated. You can say, hey, is it allocated? So it's designed to be like in DirectX is upload, read back, or GPU only. So is this memory allocated for uploading? Is it allocated to read back, or is it allocated to just use on the GPU? Bear in mind the first two can be CPU visible, right? But in Vulkan it's a little bit more silly. The types are opaque, meaning rather than being an enum of 3, it's an enum of 32. And the driver can make as many as it want, up to 32. And you just don't know what they are. Now this is great for a driver because the driver can be like, I want to make a special one, which means GPU only and only for color attachments. And that means it can put the memory in a special place and know it based on memory type. But for people writing the Vulkan code, it's really annoying because you have to search over all the memory types. You have to find the appropriate one. That's the one I want to use, and then use it. And then allocate memory using that memory type. So yeah, it's a big pain in the butt. So how we're going to solve this problem is we're just going to, right, so there's that thing. The other thing is, what's the other one? Also the lifetime of these things. So right now we're just creating buffers and textures, and these are going to be kind of like static in a way. But in the future, we can have the lifetime of these buffers could be the lifetime of a frame, meaning that the memory is aliased with other buffers over the lifetime of a frame, right? And it means that you can basically save memory on the GPU when you allocate, because effectively in a GPU, the whole job of the GPU is to take in one texture as input and output another texture. Well, guess what? Oh wait, and do the same thing again and again until you've made your final frame. But after you've used this one and rendered this guy, maybe this texture is never used again. So what you could do is, if providing the textures are basically the same size or whatever, you can deallocate this memory and this texture, but still keep the texture around, right? So you deallocate its memory. And we'll already deallocate the memory. You pretend it's free because you have your own custom memory allocator, right? You deallocate it you don't deallocate it using Vulkan. You deallocate it in your own memory allocator for Vulkan. And then you allocate this guy. And quite possibly these two textures will overlap in memory. And that means you're aliasing this maybe. the same memory, and therefore saving space rather than having space for rather than storing 3 textures, you're only storing 2, for instance. Right, and more. Oh ho ho! Thank you, Toggle. Thank you, sir. Appreciate it. Welcome, Raiders. How are we doing? Thank you so much for the raid. Good to see you, Mr. Toggle. Welcome, Raiders. How are we doing? How are we doing? So working on a game from scratch written in C. Here it is. Whoa. We've got an X11 window open by calling directly into X11, and we also have a Vulkan compute shader running using our own custom shader compiler, which compiles C code into shader code and runs on the GPU. So we're just implementing some Vulkan bits, like creating buffers and textures, so we can actually do some more fancy graphics. But yeah, hope Toggle's stream went well, and welcome everybody. If you have any questions or want to see some code or anything like this, feel free to ask away, and I'll happily explain anything. Or have any questions around graphics programming? I'll give that a go. So we're just going to allocate some memory. So we just explained that there's different lifetimes. There's static lifetimes and temporary lifetime that you might want. But for now, since we're writing a game engine from scratch without, we're gonna do the simplest thing possible to get going. We're not gonna write an engine. We'll add the feature when we need it. So for now, we're just gonna allocate the memory statically, and if we need a temp resource, we'll figure that bit out when we get there. So, right, how does one work this? So I think when we boot up, wait, what are the usage flags? Did we check the usage flags for images? Storage image transfer, we don't need any of those. Yes, right, this is good. Since we're doing compute only, we don't need any of these. Right, so this means we can hard code the memory types. This is good. Well, not hard code. We can store the memory types after we initialize the whole subsystem, GPU subsystem. So in our big GPU global variable, right, U32, memory type index for a buffer, memory type index for a image, right? And we just use those. So basically when we allocate, so for now we're just going to call that super lovely VK. Wait a minute, we want to use allocate memory 2, isn't it? Oh, did I close the Vulkan header? Allocate a memory. Oh, there's only one of those. Right, so we need to add that to our function loader. And then a deallocate memory as well, might as well. No, it's free memory. Ah, come on. Cool, let's get that in there. So we want to allocate some memories. Device allocation callback. No, allocate info. Ah, it's already got the S type in there. I see. Alloc info. Oh, did the music stop? That's not good. VK structure type. memory allocate information. Allocation size, good point. So how do you get the allocation size? So you need to query that from Vulkan. You need to say like memory requirements, that's what it's called. Ah, it's right in front of my face. Right. But we're going to use the new version of that. Memory requirements 2. It's alright, bug. I don't know why they did this. They included the old one inside. So you have to say memory requirements dot memory requirements dot size. It's the biggest, like, spammy head moment. Ah, one day. Right, get buffer memory requirements 2. Get image memory requirements 2. Very nice. Let's put these create images in here as well in our function loader. Right, back to actually writing some code. So you get some memory requirements, right? Mem requirements. Dot s type equals vk structure type. Memory requirements 2. P next is null since we don't use any extensions yet, but we possibly will do it in the future. Then that'll zero the rest of the elements. Then what we're gonna do is call that new lovely function we got. Get buffer memory requirements. This gives us back a size and alignment. So void return, so we didn't do anything special. GPU VK device. Take the address of that. Oh, we need this thing as well. Damn it. Fill this boy in as well. Ah, too many things, you know. Mem requirement info. Look at all these super lovely structures. They're just, aren't they beautiful? VK structure type. Buffer memory requirement info 2. And no, then that, the thing we did like 10 minutes ago, which was create that that buffer. Yeah, we use that, right? So it's gonna, the backend, sorry, the driver is gonna like figure out for us like what is the size and align when we get there. So in goes the memory requirement info, then in goes the memory requirement structure. So that's what we get back out. Okay. So we call that guy, get ourselves some memory requirements in here, size and align. So now we can finally call allocate, right? Allocate as an allocation size, great. Memory requirements dot size. Dot memory requirements dot size. So we could have just, so you could be thinking, right, but the resource has a size. Why can't we just use that? Well, because that size might not be aligned to, like, it might not be rounded up to the nearest alignment. So when you call this, it gives you the alignment and it will give you the size that it needs to be allocated with. So you will call that. Then you need the memory type index, which we're going to store globally. Memory type for a buffer. Yeah. So in future, when we allocate memory, we might so it returns the device memory into that back-end structure. Right, so it just has a VK buffer in there and a device memory. So in the future, we might have a custom allocator for temporary resources, and we might maybe generalize this code on it, or maybe we won't. Right? Maybe we just copy paste it and do a specific one for temporary stuff. But this is for a static buffer. So we need to say GPU VK to use the function pointer, because we use function pointers, not the direct prototypes. So we would just, create the buffer, right? Get its, what am I doing? Get the buffer's size and align. And then we want to allocate the memory, the buffer's memory, and then we bind the memory to the buffer. And when you bind it, it's now usable. Ta-da! Yeah. So that is how you create a buffer. Now creating a image is actually very similar. We got to remember to do, after this, actually find the correct memory type index. We will do that afterwards. So we're just going to search for the word buffer and give it a good old replace for an image. Now, images is a bit more complicated. We'll get to that as we go. Oh, bit too much of a find and replace there. So we need to wrap this in a union, VK buffer, and then because a resource can be a buffer or an image. So we're going to say image. Now, the funny thing is, right, an image has to be accessed via an image view. So an image view means you can basically view its sub-resources, right? You can view like the sub-MIP levels or the sub-array layers. You can sort of like do a sub-view of array layers or MIPs. But we're not going to have that probably for a long time, so we're just not going to bother implementing it. So typically, you always create an image view with your image. So that's the thing that makes it more complicated. And the fact that an image has more parameters when you set it up as well. So we'll get those sorted out. So this will go into the VK image. So let's go into the create information and give it a look. We need to do so. Right, it's got some flags. I don't think we need any flags, pretty sure. Image type. We need to translate our image into a VK image type. So as the type of image, we're going to switch on the resource type. We've got a couple of cases here. More of a public thing. So I think what we want to do is probably use my lovely macro. So we've got about 4 asses, I guess. Then anything else, I think we want to say, not HTC anymore, it's core. Texture type. So if you've got a buffer, this will be core abort You know, we won't do that. So this is going to translate into a VK image type 2D. Then this one's going to translate to a 2D as well. This one translates to a 3D. So the 2D texture array, the array part, is part of the texture view. So the image view. So we have to wait until we get there, is all. No biggie. So we're just going to flatten out to not make it so vertically fat, like me. What we're going to do is, type equal type, or image type. Format. We also need to translate formats. So to translate a format, we'll need to do that multiple times. We will just need to do it. So for that one, we're going to add a new lovely function. VK format, we're going to call it. It's going to return a VK format, and then we're going to pass in a GPU format, so that's our own custom format. We have a very limited set of formats because we don't need all of them, and it's an abstraction, remember, so it is going to be, you know, not all platforms have the same formats. So we need to get the formats. We have only 888 RGB and a separate one for sRGB. So we need to do a switch on the format. You know, it could just be a lookup table. Could be a lookup table, then it's not code. GPU format count, external. Define them above those, please. Right, let's move this up a bit, put it here. Excellent. Right, so here's a lookup table. Now in C99 and above, which makes C an incredible language, you get these things called designated initializers for arrays and structures. So we can just simply do this. And what we need to turn it into is a VK format. So the best thing is even if you reorder this enum, the lookup table is going to remain fine. Now obviously if you miss anything, it's going to return a zeroed one, like a zeroed format, but that's fine because it will catch that. We'll catch that. Hey there, Bunny Montana. How you doing? Yeah, weekend's pretty good. Yeah, it's a pretty decent weekend. It's been nice and warm. Mainly relaxing yesterday, like doing a good workout, you know. Just making sure, just feeling good. Went for a nice walk out in the sun today. Cooked a roast dinner. Yeah, it's really good. How about you? How's your weekend been? So this one's gonna be 888. I think they got that. No, R8. All right. It's playing funny. R8, G8, B8. Oh no, we got like unorm and everything, isn't it? Shoot. Yeah, I should call it unorm. Let's correct that. Cool. And then this one is going to be sRGB. There we go. So now we've got a super lovely lookup table that we can use in all the places where it requires a format translation to the Vulkan one. So right here we say dot. Oh no. All it is, we say VK format, resource texture format. Oh yeah. Sounds lovely. Here as well was Father's Day today. Nice. That's some tapas and risotto. Lovely. Now that sounds nice and relaxing. It's cool. Oh, yeah. How's the software projects coming along? All right. Yeah, I think this type one. You know, I want to rename it. I want to rename that. I want to call it VK image type. I like prefixing stuff with VK because it means you can tell if a variable comes from the high level thing or if it's a variable which is the Vulkan, meant for the Vulkan stuff, you know? So I really like doing that. So this size thing, no, it's not size, is it? Extent. So we could do a translate, since we'll probably need to do it a few times. So I reckon we can add a sort of like VK extent. For that, we'll take in a U32 times 3, which is our vector 3s of uint. And we're just going to take in the value as V, and then get back a VK extent 3D. Oh, we're nearing 1,000 lines of Vulkan code. Damn it. Right, VK dot width. You know, it's probably directly translatable, not gonna lie. But we'll let the compiler work that one out. Maybe we can test it. Or maybe we can look at the assembly or something at some point when it matters, right? And we got that there now. That is good. So for that, it's going to be resource texture dot dims. Cool. Next one is MIP levels. MIP levels. Boom. Array layers, please. That's the next one. Then samples. We're not doing multi-sampling. It says VK sample count. 1. Uno. Tiling. VK tiling mode optimal, because remember saying earlier, we don't really want to have linear textures ever. Everything should be optimal. And if we're doing linear, we're going to put it in a buffer, then copy like from CPU in the upload buffer. And then we'll copy it from the buffer to the GPU resource, right? Then the usage flags, let's plop those in there. The usage, we need storage image and transferred destination, and probably sampled actually. Color attachment. Yeah, so I think we basically need to all these guys all on there. Sampled, because it could be sampled, it could be a storage image, or it could be a I don't know if we'll ever have a sampled. Will we ever have a sampled image? Yeah, I think we might. Yeah. What is next? Sharing mode. We did that before. Sharing mode, and voila. So there's oh no, initial layout. It's never pre-initialized. So it can either be pre-initialized or undefined. So we need to start undefined. Cool. So that creates the image. Just quickly replace all those. So we've still got a couple of these to sort out, but we're getting there. Right, so a bit of a catch up. So there's the Vulkan image that gets made now. Hey there, Mr. Dick Still, good to see you. Staging for vertex or index buffers. Device local bit. So staging buffers meaning like staging for vertex buffers or yeah. So we're not using any vertex or index buffers because we're not doing any traditional graphics pipeline. We're only going to be using compute, which means it makes the whole API like a lot. It doesn't make it simple, but it makes it simple compared to if you don't use compute only, right? Yes, that's that. This is the experiment basically. Can we do compute only and find something awesome? But yeah, we'll have an up like we'll call it like an upload buffer, but another term is like a staging buffer, where we will stage it from the CPU, then that gets copied to the GPU, and that one will be device local. Yes. Oh, sorry, it won't be device local. No, device local means GPU local. No. Yeah, we still need to search for the memory types after we've made this function. Slow did another rinse and repeat the other day. Busy at work, gotta always continue sub. Oh, can't always continue sub projects. Yeah, it's understandable. Makes a ton of sense. Did you establish backend API? Yes, we have a backend. I know Perry will be impressed. So this is our backend right now. It's dead basic. It's not got a lot. It's like initialize, frame start, frame submit, and like anything in between there, you're going to do a command, your commands in between this frame start and frame end. So that's like your command buffer recording. We're not doing a 2-pass system yet. We might need that in the future, but we're going to try and avoid a 2-pass system and record directly into the command buffer for now. And then we've just added these guys today: buffer initialize, texture initialize, and resource deinitialize. We are then going to, and then like here's our front end API. We simply have like our resource one, which we've just made today, and we got commands one, which is just a wrapper around those backend ones, and we have an initialize, right? Over 100 lines of code is unmaintainable, and more than one file is a sin. Oh, I don't know. I think like if you have more files, it's just such a pain to work with. I think it's just really easy to search within a file rather than having to dart around files and find the thing. Obviously, if your text editor has like IntelliSense and all of that, you can maybe dart around a bit easier. But then you end up opening tons of files you have to close. It just seems like really silly. And then also you have to answer the problem of like, how do I split this file up so I don't go over the 100 line limit? It just seems, that seems quite unmaintainable to me. To me, it seems easier just to stick a whole subsystem for the most part inside a single file. Now, obviously, I do have like 5 files per system. In this case, I've got this main GPU C, and I've got one for each backend that I've abstracted over. But yeah, I typically keep the files very minimal and quite meaty, you know. Curious about your computer approach to rendering. Yeah, so I'm not going to go too far into it, but yeah, we're just going to be, we are going to do 3D. We're going to start with 2D to do some basic UI, but we will get to the 3D and we'll do an R&D on that. But yeah, like if I were to give like examples of compute-only rendering, you can basically ray trace, like, you know, I do have a sample of that in HCC, where we just ray trace against voxels. Like, yeah, it's not anything too impressive. We've just extruded the logo out into the 3rd dimension, and then we just treat those as voxels, and we ray trace against it per pixel. You can sort of see it, but it's, yeah. But anyway, yeah, there's grep as well. That's it. I've got grep built into NeoVim using TJ's telescope plugin. It's good. But yeah, things end up opening tons of files. I don't know. C tags. I've heard about C tags. Someone told me about them, but yeah. Oh, that's good, Mystic Still. I'm glad you're going hard with the 1,000 lines per file. I do like that, especially working with the Vulkan. Yeah, exactly. How will you split that? Yeah. Right. So, how does one move on from this? So after you create the image, you need to allocate the memory for it and bind it before you create the image view. The image view will be invalid if if the image doesn't have a valid memory bound to it, right? So we need to plop that in there. So we get the memory requirements right from the image. What is the size and alignment? A lot harder to calculate across different driver implementations, so it's kind of good this function exists for this. Then we allocate the memory using the image memory type index. Then we bind the memory. Cool. Cool. All right, one more thing. We now need to create an image view. So we need this lovely thing. And then we need basically this thing with the word view on the end and the word view on the end of this one. So remember, the image view is like a sub-resource range. We're just going to view the whole thing, and you need an image view for any image. Okay. So we're simply just going to fill this boy in. View create info. So the S type is obviously VK structure type. Wait a minute. Image view create info. Pnext is null since we don't use any extensions yet. Maybe we will. I don't know. Then we need to pass in the image that we made from the previous call to vk create image. We need to pass in the view type. So we'll say vk view type, which we'll make in just a minute. Then the format, which will be vk format, which we translated up above. Then we need components. So this is swizzling. So you can swizzle the components around it in a view, which is pretty cool. So we don't want to swizzle, so we just RGB. Then the sub resource range is the sub resources, right? So we've got the aspect mask, which would be a color. So if we have a depth texture, we might have to change this. But yeah, we'll let the color. You know, what's the let's get them in the right order. I like doing that. Even though it has no practical benefit. Base 0. Resource. Texture. MIP levels. Erase layers. So obviously if we were to create a view which does a sub portion of those, will change these things, right? And obviously if we have a depth texture, we'll do a depth bit there instead of color. Actually, because we're doing compute only, we'll never need a depth texture, because our depth texture will just be a plain old integer rather than, or a plain old float, rather than actually using a depth texture format, right? Because it's done entirely in software rather in hardware, well, rather than using the API. Right, so now we're going to make an image view. So remember up here when we did the image type, the image view type, we need to make that. But up here we did the image type, and remember when I said for the texture for the 2D array, we don't put the array here because there is no like, it's only 1D, 2D, or 3D. But the array part, or the cube part, if you do cube array or anything like that, that gets specifically just defined in the view, because you can imagine the view obviously as an aliasing a sub portion of it, and you could interpret a 2D image as a view, as a 2D array, or a 2D cube, or not 2D cube, sorry, I mean like a cube or a cube array. Yeah. So this will be a view type, and the view type will simply be view type 2D, view type 2D, 3D. This one will be 2D array. Now you also have cube and cube array if you have cube maps, but we probably won't need those. If we need them, we'll throw them in, right? But it just keeps the code base better that way. Right, so that should be everything, right? Sorry, that creates a texture. So it's quite a bit of code, right? You don't want to be doing this all the time. Hence why we've, made it a lot easier now. It's now like one line of code instead of all of this. So that's super nice. So yeah, what's the next step? So we actually So let's make a function. So in the internal Vulkan, we're going to do a thing. And that thing is memory type find. So do we, yeah, I think we want to have like a find. Huh? Yeah, all right. So if you remember me explaining earlier with Vulkan, there's in if you're programming for against a DirectX or you're programming against Metal, there's basically three memory types. There's upload for uploading, so it's memory specifically for uploading to the GPU. There's read back, and there's GPU only. The first two are what's known as host visible, meaning the host can, the CPU can read them and read and write to them. And but also all three of them are GPU visible, right? They're GPU accessible. But in Vulkan, what they did is they were like, we're going to be difficult and support all of this hardware and give the hardware the ability to optimize specific for their needs, so that it's going to be a massive ball ache for the user. So what ends up happening is we now have 32 memory types, but you don't know what they are. So what you have to do is you have to locate the one that you want. So to do that, we need to what's known as look through the memory properties. And it's basically just an array of it's a bit of a gander. Right, property flags, this is it. So there's different heaps and there's types which link to a heap. And a heap is obviously a big wad of memory. But yeah. If you guys want to know anything about Vulkan, like, what did the GPU info, yeah, I highly recommend vulkan.gpuinfo.org. It is a savior for figuring out what the hardware does for this stuff. So it tells you about extensions, tells you about features, tells you about what formats are supported. It basically scoops up all the support, because in Vulkan it's just so, like, devices can support whatever they want of it, and it's so flexible, tons of options. It's a massive pain. But if you go to a device, say if we want to look at the GTX 1070, we can take a look at that, look at one of the driver versions on Windows, that one was. Look at the memory section and it tells us everything we want. So there's 3 different heaps, it's saying, I think. No, it's 2 heaps. No, 3 heaps, I was right. So 3 heaps, and each heap has its own memory types. Bear in mind, these would all... You have 32 memory types, so this will be 0, this will be 1, 2, 3, 4, 5, 7, 8, 9, and this will be 10. It's just the way they've organized it here, but as you can tell, this heap is device local, meaning it's local to the GPU. That's what device means. And host means CPU. So this is some 8 gigabytes that's available to the CPU to allocate. And this is where your staging buffers can go, or your readback buffers can go. And it gives you some flags like host visible, say obviously the CPU can read it, and coherent, which means that you don't need to tell it, you don't need to invalidate any caches, CPU or GPU side, or flush caches or whatever. And cached means that it's better to read back on. So you would so if you allocated memory with memory type 8, it would be optimized for reading back because it's cached. Whereas if you have 7, it's more optimized for uploading, right? So Vulkan basically, like, in a very complicated way, implemented what DirectX has. Yeah, it's a pain. For reasons as well where they could use these ones here. No, the music stops. I heard that one. They could use these ones here for whatever they want. See, they're none. None basically means... Oh no. Ignore me. But yeah, when they use them for nothing, it means they can use it for something that's kind of hidden behind the scenes that isn't quite expressible through the limited number of bit flags that they've got for the properties, right? So if they had it on the device local side of things, right, the device local heap, they could have a whole bunch of extra ones here, and they can use it behind the scenes to say, hey, color attachments needs to be allocated with a memory type of 1, for instance, right, on this specific GPU. So this is memory types. They're complicated and annoying, but yeah. So we need to find our memory type index, which has device local, yeah, and something else. Hey Dr. Wolf, why do people from Norway so good at editing files in Linux? You think I'm from Norway? Oh, good joke. They're Vikings. Ah. Good joke. Oh, Nico. You're taken out by a bot. Yeah, so they're like VK property flag thingies. So here they all are. There's some extra ones, extra bells and whistles for specific hardware. But anyway, we don't care. So what we're gonna do, so I think we need to also support what is that function? There's a function where you can get the memory based on the memory type. I think you can get whether or not it's supported. I think it uses the buffer create information. Or uses a slimmed down version of it. Right, it's not the usage flags then, it must be the full create info. Yeah, device buffer memory requirements. So you can use this to check. Yeah, like basically if you read the Vulkan spec, if the usage flags change on the buffer, it could be on a different memory type. So if the usage flags are the same, it means the buffer will have the same memory type. That's the way the spec reads. And the image one is more complicated. And it never guarantees that images and buffers can be on the same memory type, even though they quite possibly always are. It's really annoying. So basically you can get back memory. Oh, you're the memory bits. Oh, yeah. Man, this is gonna be good. Right, so the function we want to make is we're going to have some sort of like preferred flags. We're going to have some... Wait, I always forget you spell preferred. I think it's 2 R's. Yeah, it is. Good old Google. Preferred... Required, I think. Yeah, required... Preferred, required... And then ones that we want to sort of like... Ones that we want to like... Like, ones that we want to like avoid using. All right, trying to think of a good name for this one. So these are the preferred memory flags that we want. If we can't get those ones, we get the required ones. And if we can't get those ones, it's a fail. Then the other one is like, these are the ones that we do not want, right? So these are undesired. But undesired is like, VK whatever flags. See, not wanted. It's not like it's not wanted. It's like... There's a good word for it. Required flags. Preferred, required, or like... Yeah, I've already got preferred. Oh, what is preferred? It's simply just like we prefer these memory types. So you might want to have device local. Sorry, you might want to try and find a memory type. Oh, where's it gone now? You might prefer host cached, but it's not the end of the world if they don't have it, so you'll fall back on coherent, right? That sort of thing. So these guys will be required for a readback buffer, but these ones will be the ones you will prefer with a readback buffer, right? Then these ones will be like, I guess, not preferred or not wanted. Request reversed available. Kind of. So we want like an undesired. We want like an, I guess we could say avoid. DK avoided flags. Yeah. Let's just do that. So we need this one. So we need to search for all of the things. So we also need the memory type bits. This gives us all of the bits. So this 32 memory types, it's a bit set for all of the, for each memory type which is supported for this buffer or image, and we will search for the right property and then find that one, get that one. So there are two hard problems in computer science, namely things, cache invalidation and off by one errors. Aha, good joke. Off by one error, get it? Yeah, it's so easy to make an off by one error, especially using Lua. Right. So before we go and implement this, let's write the usage code. Shall we? So we need these two lovelies. These go into our super lovely lookup table. No, look, sorry. These go into our super lovely function loader. That's the word I was looking for. This is a jam. So what do we want to do? This is kind of in like when you're loading it, isn't it? So I think we're just gonna, we won't really need these too much. Okay, so we load those boys up, and what we're gonna do, when we do a GPU backend initialize, so, excuse me, after you allocate the, well, probably do it right at the bottom. We're going to make ourselves a so many bloody structures. And then we need the memory requirements too, isn't it? Oh, bugger. Yeah, this one. We'll get that back. And then that'll give us the memory type bits in there, right? So, yeah, get memory type properties as well. I need that one too. That's right. We'll need that inside the function. Yeah, no, yeah, I think we've already loaded that globally, I'm pretty sure. We'll have a look. So you need, this is the return structure. Oh, such a pain in the butt, all this. Nearly there. VK device buffer memory requirements, null pointer there please, at create info, voila. Find the buffer memory type indices. So what is the size? We'll just put like 64 in there, right? It doesn't matter. What matters is the usage flags. That's it. So we just need to keep those. No create buffer. We're not doing that. I'm gonna say create info S type. This one will be the memory requirement info, I guess we'll call it. So we call this boy, pass in the GGPU VK device, pass in an address to the information, pass an address to the memory requirements, get that back out, and it returns void, which is cool, so no return arguments. GGPU Vulkan, call that boy. Right, so this gets us back the memory requirements. So now we need to actually use that lovely find function we're about to make. Just remembering all this makes me want to, yeah. It is so much work. So I think when we do a memory requirement find, I think what we're going to do is, like, this must exist. So I'm going to assert when we inside this function, it's never going to return anything invalid. GGP Vulkan memory type. For a buffer. Then what we're going to do is pass in the memory type bits. We got that back in that memory rec dot. See this memory requirements bit? There's size align and there's also memory type bits, right? So in the old days before we had this API, what you would have to have done is create a buffer, right? It didn't worry about allocating any memory, just create a buffer, then call the memory requirements function for that, then destroy the buffer. But now you can do it this way, which is good, since Vulkan 1.1. So there's preferred flags. So what's preferred about this? Good points of look. Memory property. So we prefer, well, we don't prefer device local. We require device local, right? And we want to avoid. Let's have a, we need to have a look at them all. So we want to avoid. No, it is undesired. Wait. Yeah, I think it's undesired what we want. There's not preferred. Avoid. Yeah, I think undesired is a better name. But avoided is a good name too. Yeah, but avoided can make it seem like they're always, but undesired is the better name. Because undesired will mean you don't want it, right? But you can have it, right? Much better. So, all right, this is where we're going to put some comments in because it makes readability way better. So put some comments in here for all the. This song is a jam. So this is the preferred flags. No, my battery's low on my phone. Alright, let's get you guys charging. Fallback. Well, it's not really fallback though. You're specific. Yeah, I guess you could do like a fallback method, right? But yeah. But yeah, I remember reading about this approach from, I think this was from the guy who ported Doom, like an old Doom to Vulkan. He did like Doom VK. And I remember reading his blog and I was like, it's quite a decent way of doing it. I'm not sure where that blog is anymore because I've not seen it for a long time. This was back when Vulkan 1.0 was a thing. Undesired flags. Right. So what do we sort of like, what do we prefer from this? So So I think we prefer 0. No, we don't want any. We have no preference. Yeah, we have no preference in this case. We require device local, but we want to. What's undesired is host visible, right? We don't want, because it's possible to get host visible device local memory, meaning it's possible to get CPU that is apparently local to the GPU, but the CPU can write to. But we typically don't want that if possible. If you use like rebar when you use rebar on like an AMD GPU or whatever the NVIDIA one is, your whole GPU can be host visible, pretty much. But yeah, typically we want to search for those. Yeah, and then right, so that ought to be good enough. And then we do the image one, and these will obviously locate our memory type indices that we use to allocate our buffers and images with. Hello there, Master Ride. I'm coding in Vulkan as well, right? Nice. So you're doing some Vulkan programming. What sort of thing you doing? What sort of application you're writing? Is it a game? Buffer. Image, create info. Let's get this right. Ugh. Wait, we need to fetch the image, create info. Let's just fish out the whole thing. And for this one, I believe the format has to basically be the same. Wait, is that right? Oh no. No, it can be a color. Yeah, yeah, yeah. So the Vulkan spec reads if it's a color format. So if the color format differs, or if the tiling differs, or if the usage flags differ, then the memory type can be different. But if the format type is a depth texture, then the depth has to be the same. So what's interesting is we're only using color. So what we can do is we can put any old color in there. So we can say, wait, where's the format at? Wait, do we miss the format? We missed the format, guys. Shoot. Huh. Whoops. Yeah, I like putting it in order, so I was just checking. So this one could be any old one, so VK format RAGABA, you know, right? You know what? Let's grab that line. Vulkan. The spec states any color format and matching usages and matching tiling mode get the same memory type index. So we won't ever do anything else from that. So dimensions, we're just gonna do 1 by 1 by 1, which is completely legal, doesn't matter as well. Memory type, sorry, 2D, cool. Levels 1, array layers 1. Same flags, nice. Yeah. So we fetch the image memory requirements, then use the memory requirements thing we've just fetched out, use the bits, right? And this one goes in. Oh my days, that's his. No way. Can't believe I bugged that one up. That's fine. What about the image view? I don't think we did the create. No, maybe we did. Right. Image. So this one wants the same thing. Device local, not host visible, please. Right. Yeah. So now let's go and implement this function here. This is where the fun begins. We get to use an intrinsic. I love this intrinsic. We get to use it. Yeah. Too many people don't know how to see, you know? Making huge. I'm making a huge wrapper made Vulkan easy to implement instancing. Cool. Is it? What's the camera looking like? Yeah, we need to turn a light on. Yeah, I remember doing that before. Like, yeah, Vulkan's a pain. But yeah. It's, yeah. Right, so here what we're going to do is we're going to loop over all the bits and find an index. Right, we can use count leading zeros or trading zeros, whatever which way around it is. We're going to get that. Oh no. We have that on a maths library already. What's it called again? Third party, HCC. No. HMaths. No. libhmaths. Huh? Scalar. LSB. Bit LSB, yeah. Returns the index of the least significant bit. This is what we want. So good. So it's basically like count leading zeros or trading zeros. It's like a single instruction on x86 and ARM. Super handy, super awesome. Yeah. So what you can do is you can fish out the memory type index like that and do a lovely while loop while you have some bits in your bobs. You can then remove the least significant bit by saying an and equal of that take away 1. Pretty sure. Remove LSB. Least set bit. So there's a lovely iterator. Iterates over all the set bits in a bit set. Pretty sweet. Include me some HMaths scalar for me, please. So now we can simply check our memory type properties and see whether these flags are what we want. We'll be uploading it to YouTube. Yes, Brave Teddy, this will be on YouTube. And damn straight here, Nick Johnson, here's the man. I keep forgetting to record locally, you know. This is not good. Things could go wrong and then I lose it, but luckily the internet connection is good. But not so much my green screen anymore. Welcome there, Volatile Majesty. Right, I'm going to take a quick 2-minute break. I'm going to switch this light on and everything. Get another drink. It's bloody warm in here. We're going to use this super lovely iterator here, which iterates over all the bit sets in a super great way, and make sure and locate the type that we want. Bear in mind, we also want to do some form of abort here. Like we failed to find the bit set. Right, but yeah, I'll be back in a couple of minutes. Oh, just knocked the microphone. Right, enjoy the tunes while I'm gone. Alright, welcome back everybody. How are we doing? How's it going? Right, I got me some snacks. Got the light on now. It's probably gonna get really warm in here. Got some mixed nuts, you know. Right. So what I plan on doing is writing this guy. So we're gonna assert here if we can't find it. Because we need it to work or we can't support the device. So it would be better if the error is done it'd be better if it finds this while it's trying to look for support for a capable GPU. Yeah. Maybe let's return all the bits on. You know? Screw it. Right. So I need the memory properties. VK, physical device, memory. Oh, come on, IntelliSense. That's the one I was looking for. Right. We need this one. There's a 2, I think. Yeah, we might need that because you can daisy chain and get extra bits back. I think we'll do this one. But memory properties. So I think we already have one of these laying about. Yeah. So we have in the global VK structure, when we create the device, we just put it in there. So for this, we can simply check. Let's do that. Rightio. So in here, it's basically filled with a bunch of lovelies. It's filled with all the properties, right? These property flags. So we simply just need to say, right, if VK, wait a minute. These are the found flags. So these are the flags we've found, VK flags. So this would be VK memory properties. Deref, obviously. Memory types. Memory type index. Yes. Dot property flags. So now this is where the magic begins. So you say VK flags. So if, right. So in the first loop, what we're looking for so we need to ensure that this So we have a little go-to there. So if we can't find the required flags, we're going to go to the next memory type here. So in this one, we're trying to find the preferred as well. So in this one, we say we prefer if it doesn't have the prefer flags, we skip. Then in the next, and also, we called them avoided here? No, undesired, wasn't it? That's what we want. So the undesired flags, so these ones like you don't want, right? So if it contains any of these, like any of them, we also continue. Now if we reach here, we win. Right, I guess I could make this a for loop. I've basically just made a for loop, haven't I? Like, it's the same as doing that, basically. I don't know, maybe it's less readable. Yeah. You're married last year. It's nearly a whole year. Next month. Well, 1 month and a half. Hey, Swank Funk, how you doing? It's been a while. How you been? So yeah, I could do the for loop syntax, but it's just not worth it. Right, this is more readable. Now here we're going to return memory. Yeah. Now, if that fails, we got one last chance. We go over it again. Problem is this mutates it, isn't it? Thank you, thank you. I've also got a baby on the way, a little baby boy. He'll be here in 1.5 months. Yeah, so I think in the past I've written this with just a for loop, but now I'm doing it with count, like I'm doing it with these significant bits, so it's a bit weird. You know, the for loop might be better, more compact. You know, let's rewrite. Let's do the for loop. For remove LSB. There you go. Yeah, slightly less readable, but oh well. Then at the end you return. Ta-da! It's quite a good iterator, really. There you go. See, we could make that to a macro, you know. We could say like for we could just have a 4 macro which is like 4-bit set. But yeah. Interesting. Wait, but it does mutate the bit set. Hmm. So you don't want to do a backup. Wait. Bits. All the bits. Oh my days. This is I'm not sure how much harder it is to read now, but anyway. Oh well. Right, so in the second approach, right, you say you try to find the preferred and avoid the undesired. And then in the next one, it's like so you loop again, and this time you probably want to remove maybe all of these two and just do a required one. And that should be it, right? Cool. So that is gonna compile now, I think. Nearly. Oh, yes. Okay, so now we've implemented creating buffers and textures. But to use them in the shader, we have to upload the descriptor set. So we have to upload it into the descriptor set. So we could write this code. Let's read the docs for this. What happens if the descriptor is null? Does it like it? Wait a minute, it's gotta do this. If null descriptor is enabled, the buffer or acceleration can be null. Right, but I don't think that's supported too well. It's an extension, I think. Or is it a feature? Wait, let's search the header. Robustness 2. Interesting. Did that get made into core? Robustness 2. Oh, come on. I'm pretty sure that got promoted to core. Or 1.1. Null descriptor says, oh, come on, it's not even there. Oh, wait, it's not saying promoted. It's still an extension. Crap. So robustness 2, is that still not? Yeah, because if not, it'd be somewhere else. That's not good. Hello, Vulkan. Yeah, so the problem with OpenGL is it's too it doesn't map to what GPUs are nowadays. The problem with Vulkan is it's so general and complicated that we've literally taken one line of code and turned it into like a page or two of code, of Vulkan code, right? So there's quite a lot of stuff that goes on. You can use WebGPU, and there is a native C bindings for it called WGPU. I think it's written in Rust, right? If you're still learning graphics programming, this is probably a good shout. The only problem with it is you have to use their specific shading language, which isn't amazing, but it's probably okay enough if you're learning, right? But yeah, after you've learned this, you can take a dive down to Vulkan, basically, or you can go back and watch all the stuff we've been doing on this project, which is only 2 streams really, plus this stream, and you can learn how to do it with compute only. But yeah, it's quite a bit. Yeah, I'm not sure if people I'm not sure if anyone actually likes Vulkan, but you kind of have to do it. You know, it's just one of those. So we'll upload our descriptors. We can't use the null descriptor unless that null descriptor thing is set. Oh, finally this thing's loaded. Robustness 2 is like 36% support, so we're not going to use it. So it would make it really easy if drivers just could all support null handle, meaning we can just have a big wad in memory and just like poke them CPU side and just go, there you go, driver, boom. But we have to write the optimized way by getting our descriptors, like going over all of our resources and uploading them. So I think what I want to do, I think I want to wait. Okay, I think I want to surface resource, right? So I think I want to wait before we actually try and use these things and test them out. Because the idea is, oh, I nearly stopped. Oh, so close and he stopped streaming. I thought that music stopped. Right, okay. Is it delay? A little bit. But yeah, so basically here we want to wait until we've got our object pool in so we can go and do it properly, because if not, I don't think it's going to be... Yeah, so I think we'll wait until we actually get these things fully in. But they're basically done now. We just need to get the object pool in, I think. Yeah, bigger one. Yeah. Yeah, that's right. Yeah, I think the biggest pain is like all the synchronization stuff as well, though. There's a bit of a pain. Very easy to overcomplicate everything. But yeah, maybe yeah, start with WebGPU, Alparkin. Okay. So what's the next thing we're doing? Synchronization. So I could, let's just get this thing compiling first. So what? We need to include libhmaths. Huh. Oh wait, hmaths. We had that the whole time. I didn't have to go through the interop. I could have just done such a scrub. Right, there we go. So if we press F5, it now compiles, and it still works. So we can't test out the buffers and images we've just written. We've got to do some other bits, and then we can bring it full circle and see it all working. But it was a good endeavor because we will need it, and it was a good thing to get all that done in one stream, basically. So the next thing we need to do GPU H. So we've done that one now. The other one is syncing resources and inserting barriers, and then we need to add a way to upload to buffers and textures. So if we did an upload buffer, we can really test it. Yeah. So I think we should start with sync code. We'll do sync code, upload buffer, object pool, and then that should be most of the things we need, I think. And memory allocators. Right. And then that'll be everything. So syncing. What do I mean by syncing? So basically in Vulkan, if I were to simply dispatch two compute shaders one after the other, they could both run at the same time in a way, because you execute groups. Oh, the quiet thing again. You execute groups of you execute groups of groups of threads that run in lockstep that execute a part of a compute shader. And obviously when the compute shader is basically done and only got a couple of compute units it's using that run in lockstep, the GPU is obviously going to schedule the next task to go ahead and spawn its compute units can spawn it part of its compute shader on those compute units. So these two could be running at the same time, right? So the way you get around that is you need to place barriers. So to place barriers in, it would be a bit of a pain because the barriers, or the sync code works slightly differently in all the different backends. So what I think we want to do is add a way to say, hey, we are about to use this resource. So we're going to say GPU sync resource write only, and we are writing to the display or the Windows surface, right? And then we also say that for this one as well. And then when we call dispatch, it does a quick check and it's like, right, for all the things you've explicitly synced on, are any of those, like, did the previous command, like if the previous command did a write and you do a read or a write, it will be like, hang on a minute, you have to put a barrier in here. So it would put a barrier and stop any, it will wait for all the previous stuff to stop before it'll dispatch your thing. So I think we can do that. So, oh yeah, I believe someone said about, will this be on YouTube later? Let's drop a link in there. There's our VOD channel, if you want to catch up on past streams. Also have a YouTube where we post summaries. And there's a Twitter where I post stuff when we have more visual things. So, alright, and there is a Discord. If you want to come and chat out of stream time, or ask more questions which need more context or long form conversation. Okay. So let's design the API. So we call this the synchronization code. So so there is a thing to also say is, no, I think this is fine. All right, there is a level you can extend this in the future. You can build what's known as like a render graph, frame graph, or work graph, whatever you want to call it. And basically what you're doing is you record it into a separate array, and you don't record it directly into the command buffer like we are about to do. You put it into a separate array, you go over all of those linear set of commands, and you build a tree out of it. And then you can then reorganize things and emit them you can emit them out into the command buffer in a better way, and also do better sync code across platforms as well. But in the future we can do something like that if we need it, but for now we're just going to do the simplest thing and avoid doing that entirely. So I think we're able to do this because we're using compute only. I think if we did the classical render stuff, it will require a lot more arguments to go into here, I think. No. Actually, no, it shouldn't do. No, wait, ignore that. Right, so we're going to have a command sync resource. Oh, we have an access type as well. Type def uint GPU access mode. Enum GPU access mode. So there's a few ones you want: read only, read write, write only, and there's another one that you typically want. Like maybe you're writing to a resource, but you're writing to different parts of the resource. So technically they can both run at the same time. They can still both run at the same time. Or you're reading, or you're reading from one part of the resource while writing to the other part. So typically, like, non-alias, like, like aliased or overlapping or something like that. Like, what's a good name for it? So read only, write only. So it will not put a synchronize. It will not put a barrier in unless I think it depends on the implementation, really. So yeah, so aliasing would mean you would write to the same memory, basically, isn't it? Let's see. Let's look at definition of that. It means you typically have a pointer to the same memory, isn't it? Hmm. Maybe overlapping is a better word. Yeah, right, only no overlap. That'd be good. Excellent. So, I think it'd be good to say we've got this GPU resource and this sort of access mode. And then probably we just want to like inline a couple of things to make that more convenience functions, you know? Maybe skip it. Yeah. Partial. Right, partial. Yeah, partial makes it seem like you're not writing to the whole thing. But yeah. It is an optimization. Gotta go. Right, see you later, Nico. Good to see you. Just popping by. Have a good start to your week. So yeah, got some nice convenience functions there, which will probably just static inline. Should we do that? And I could equally just make them macros to make it just more shorthand. Yeah. And then they actually get forced inlined. Far less work. Good old C programming. RW. RO. There you go. Right. So now you got these guys. That's me good to fun. So let's get these going. It's going to be super amazing. So here, what do we got to do? So we want to store internally some form of state to say, so you're going to go over So you're going to track all the sync state, right? So you're saying I have a is sync resource a good name? It's like it's the synchronization state or resource sync. Resource sync. You know, I've seen a name like tracker being used, but it's not really a barrier just yet. It's not a barrier. Yeah, it's more of like the tracking state. But yeah, I've heard it being known as like sync track or whatever. Like sync tracker. and basically they have they're tracking. Yeah, I've seen it known as like sync tracker. And you have like a track, but the tracker makes it seem like something that's actually going around doing the tracking, but it's like it's sync state for a resource. And I hate using the word state. So I'm actually resource GPU sync resource. Oh, it's the difficult thing naming things. I might put sync state. Screw it, we're calling it state. I hate doing it, but we're doing it. So in here, it's simply like the arguments we just passed into the function and maybe more. Now let's roll with this. So simply we're just gonna have an array of these guys, and again, we probably want to like dynamically allocate this. But for now, make dynamic array when we have the memory system. Custom memory allocators, there you go, bam. So basically we zero this guy, right? Does that make it read-only? Yep, that's fine, perfect. Read-only and a null resource. That's what you want. So when you start a frame, I knew it was going to be added more to this. You zero. So I've got a core 0 element many GGPU. Yeah, I want to try and make it so it's easy to me to change this, but to be replaced custom memory system, right? There's no memset? Sad. We should forward declare memset. Maybe, you know. Otherwise I have to include like yes, the string library. Maybe this is bad. Let's see what happens. Let's see if the computer likes it. Maybe source core. Like, I have a feeling this is gonna be bad. Maybe we write a custom memset which basically calls the original memset, like, and same with memcompare. to do maybe the core compilation unit. Cube, let's see if that works fine. Right, so remember to set all those boys at the start. Nice. So what we're looking for when we do this sync is simple. All we do is we say, right, if, wait a minute, I don't need the resource ID because it's a lookup table, right? I need a function ID index gets the index from an ID. This would be a really good one. Wait, is that on the internals? What are you doing there? We'll see, probably more down below. Well, yeah, I think it might be specific to this thing. So for now, we're just going to return that takeaway 1, but in the future, it might be something else. You know, change when we have the object pool. So we've got this function now, so it avoids duplicating that code everywhere and tracking it down. So we basically want to say, right, index into that array in ggpu.sync resource states. But maybe it's just like an access mode. But anyway, let's do that. So call resID, right? You get your super lovely oh, I missed that. One of these. Sync state. And what you're saying is you're gonna say if, like, so you want to say if the previous one is writable and yeah, if the previous state is writable, well, it's a specific type of writable, isn't it? Just saying if the previous one is right, if the previous dispatch basically wrote to this resource, so if the previous one is read and the new one is write, you don't like you want to put a barrier in there, obviously, right? And the same if it's the other way around. So if there is a read and there is a write, so basically what we're looking for is if they're both readable. If one of them is writable and if one of them is writable and the current one is not the overlapping one, then we've got problems. Problemos. So we need a couple of handy convenience functions. So this one we're going to say access mode is readable. And probably could just be a lookup table. So Boolean, I guess we'll do a count. Is writable. Then we'll chuck a couple of externs on here. Grab these lovelies. Go to the frame start. Drop them up there. And then we want to get these guys, drop them, and 4 at t's. Oh. And then this one is readable, yes. See, we could have made this into like, we could have simply just made this into a bit set, a constant number. That would be so much more fun than a lookup table, wouldn't it? Screw lookup tables. Like, you can literally just do this. Access mode is readable. This is where the fun begins. But it's completely not safe. But this is where we like to roll, I guess. Warning. Do, like... Be careful changing this enum as do special bit magic. Anyway, as we were doing, special bit magic. So access mode. So what you're looking for is like, you're basically saying like, right, and this with special bits. So I guess we'll be able to put, you know, but this is 0. No, this is. Wait a minute. It's not. Yeah, we've got to define it as some. Well. We could just say read bit, write bit, no overlap bit. So like we only need like 3 bits there. And so we could say 0x, get rid of that then. 0x4, right? Then this one is just the read bit. This one is read bit ORed with write bit. And then we can simply just check. Write bit ORed with overlap, no overlap bit. Right? Quite interesting. Cool. So count is not really there anymore. So you can't really go over and iterate over those, but I think that's fine. And now we can check if it is readable, writable, just by doing an and. But to make it easier, I think we'll add this thing, because then we can simply get it. Yeah, we don't have to pull the extra parentheses. Like we know we're going to put the parentheses around it, rather than when we're typing it, we'll have to put the parentheses, like add them afterwards, right? Writable. Does it have the right bit? This is good. And then the other one will probably say like no overlap. Now, no overlap is like, you know, technically. No, it's fine, it's fine, it's fine. Right, that's good. That is good. So what we basically want to say is, hey, if the previous sync, so sync state access mode is writable, or the current one, so the current one is writable or the old one is writable, and like, so you're also saying like something like this. If not, no overlap. Yep. Then this would mean your current resource needs to be, no, your next dispatch needs to have a barrier of some kind. So it's not, yeah. So what you'd do then is say, you'd say we need a barrier. So this is what it was used like before, and this is what it's going to use like, so before and after access mode, right? So yeah. So I think the sync state after access mode gets set to access mode. Maybe we all the bits on, I'm not quite sure. So entity. Right. Right, so I think it's a good place to put it here actually. Yeah, because we've still got a bit of playing around to do. But yeah, essentially we have an idea, right? If we get into here, you know, the next dispatch needs to sync on this resource. So we add it to some form of array or something, and then maybe later on it gets cleared up or something. I'm not sure. But yeah, then in here we'll need to check that array and say if needs sync. We then will call out to some form of barrier, right? Some form of maybe resource barrier, They call it pipeline barrier, but I call it resource barrier. Yeah. Yeah, we need resource barriers in this. So we'll somehow populate that as well, right? Yeah, so that will be the sync code. We just got to obviously wire up the rest of the system and do the back end side of things as well and explain what the way you do it in Vulkan. Yeah. All right. So what we'll be implementing is pipeline barriers. There are things called split barriers and stuff like this. But yeah, pipeline barrier is just the easiest thing to implement for now. And I think it varies across hardware which one is better. So it kind of doesn't matter what we implement now. Right, so let's find somebody to raid. I'll next be on Tuesday at 6:30 p.m. GMT, and also Thursday at that same time. GMT +1. And then Sunday, same time. Actually, no, I won't be on next Sunday. I'm busy. I've kind of posted the links lately, but yeah, come hang out in the Discord, and there's YouTube and there's Twitter as well. Thank you, Not So Red. You have a good night too. Really appreciate you coming. Hope you have a good start to your week. Oh, this Ask Jesus is so good. It's amazing. Right, let's see if we can see the seas. Oh no, we got him. The Nez guy, we raided him last time. 6502. This should be like every child's first language, Awesome, I'm glad you enjoyed it. Campaign, thank you. Have a good one. Alright, good progress today. I'll see you all in the next one we do some sync code. Have a great start of the week. See you later. Bye-bye.